Hello, I'm Bert Chandler, and I have the privilege of introducing Clay Brassfield, who's going to give us a discussion on the ceramic materials development for the Aircraft Nuclear Propulsion Program. Clay?
Thank you, Bert. 50 years have elapsed since the start of the effort to develop and build a nuclear-powered airplane. The awesome amount of power which could be produced from fissioning a small amount of uranium-235 suggested the potential of virtually unlimited range, thus providing the United States Air Force with a tremendous flexibility in the use of such an aircraft. Before presenting the specific ceramic materials R&D, it seems appropriate to briefly indicate the status of materials science and nuclear technology as they existed 50 years ago. Beyond a doubt, both were in their respective infancy. Nuclear technology existed mostly in secret reports of the Manhattan Project, and with the relatively few engineers and scientists associated with that project. Nuclear technology was alien to most ceramists, metallurgists, chemists, etc. Terms such as thermal neutrons, fission cross-sections, criticality, critical mass, moderator reflector materials were new. As a consequence, there was a reliance on the more knowledgeable nuclear physicists for selection of potential acceptable materials. Materials science, as a separate discipline, was just starting to be introduced into the curriculum of engineering schools and universities. Almost no knowledge existed on the behavior of materials subjected to the nuclear mechanical thermal stress environment that would be expected in a nuclear reactor suitable for aircraft propulsion. It was the day of the piston engine, jet engine technology accelerating and requiring materials capable of providing higher and sustained temperatures if its potential was to be realized. Use of brittle ceramics in a dynamic environment, mechanical thermal stress, thermal cycling, vibration, etc., was literally non-existent and is still very limited 50 years later. The computer age was a few years in the future. It was the day of the 7 to 12 place Monroe and Frieden calculators, vacuum tubes, personal computers barely imagined. It was in this overall technological atmosphere that the need for nuclear energy for propulsion of aircraft was born. Obviously, materials capable of operating at high temperatures would be required. In addition, the nuclear physicists desired materials having moderating capability and low neutron absorption. Materials with potential to fulfill these criteria were mostly in the beryllium family, beryllium carbide, the beryllium carbide and graphite, graphite itself, beryllium oxide, and silicon carbide. Silicon carbide is not a moderator as the others are, but it has excellent oxidation resistance and was considered as a potential fuel element. It was hoped that these materials would be operable in the 2500 Fahrenheit temperature range, and the beryllium-based materials were capable of being used as a moderator and reflector material as well as the graphite. The relative moderating values for some of the beryllium-based materials are shown in this chart. What we have here is 88% beryllium carbide with 12 carbon or graphite. Took 46 pounds for this particular reactor. And the 70% beryllium carbide, 105. The BEO quite a jump to 140. And zirconium berylide, 115. And beryllium metal by itself, 110. Now this actual calculation was based on a square cylinder sodium cooled, but the relative value for the various materials would have been the same for an air-breathing reactor. Beryllium carbide was at best a laboratory curiosity. Subcontracts were placed with Battelle, Fan Steel Metallurgical Company, and Brush Beryllium Company to synthesize high-purity beryllium carbide in modest quantities. The two routes for production of it at Battelle were the react beryllium metal with carbon, and at Fan Steel to react the beryllium oxide with two carbons, giving the beryllium carbide plus CO gas. The early production material was only about 96% purity, the main impurities being the free carbon, nitrogen, and oxide. The nitrogen was particularly undesirable because nitrogen has a large absorption cross-section for thermal neutrons. Nitrogen also has a large absorption. Nitrogen also inhibited fabrication. Much of the early effort was conducted using this material. By late 1950, Brush was producing material using the metal-carbon reaction of greater than 98% purity with relatively low nitrogen. The way that you could fabricate these materials, NEPA was hot pressing billets and diamond sawing and grinding to get shapes for mechanical tests and plates for coating studies and what have you. And Battelle was isostatically pressing and sintering and large billets, and then they would diamond saw and grind also. Sintering of the beryllium carbide was really never successful. Densities around 90–95% at best were obtained, and later on when we started adding graphite to it, they were even lower. On the beryllium oxide in those days, there was no really highly sinterable beryllium oxide available. The material was really good purity, but it wasn't very sinterable. Silicon carbide was only fabricable to any kind of a density by hot pressing. One of the big concerns for the ceramic as a fuel element was the ability of the ceramic to withstand the thermal stresses generated under the high power throughputs that were going to exist. And the calculations at that time showed that the ceramics were going to be subjected to around 35,000 to 40,000 BTUs per hour per foot. And that was quite concerned. The test people developed a test for evaluating thermal stress, which consisted of a thick-walled cylinder of the material with a water-cooled tube going through the bore and the outside of the cylinder heated by radiation. Then the mass flow and the temperature rise gave the power throughput. The beryllium carbide, 100% beryllium carbide, failed at a throughput of about 3,500 to 5,000 BTU per hour per foot, which was about an eighth of what it what it would need in the reactor. And there was quite a study on additions to beryllium carbide, but the only one that was really successful was a 30% addition of graphite, and that composition withstood 35,000 BTU per hour, so it was close to what it needed to be, and that became the composition that practically all the studies from then on were on. The other drawback to beryllium carbide, and particularly the beryllium carbide graphite, was the requirement for a coating because they were not oxidation resistant, literally burn up whenever they were heated to the 2500 F temperature. There was a pretty intense effort conducted on these materials, and about every coating system that you could think of, ranging from platinum, metal cermets, metal mixtures, vapor deposit silicon and silicon carbide, and glass-based enamel glazes, to name a few. Almost any combination deemed to have the potential oxidation resistance at 2500 F and above. While some coating systems provided protection for some test specimens for as long as several hundred hours at 2500 Fahrenheit under more or less static conditions, none of the coatings or coating systems were reliable. Failures times range from almost instantaneous to a few hundred hours. The most successful for the beryllium carbide were the ceramic glazes, and for graphite and silicon carbide and siliconized silicon carbide. This is typical of a glaze composition that was used on it. It has about 50% silica, 20 to 30%, 20 to 10% calcium oxide, and then the various other oxides. Those are a little different from normal ceramic enamels in they are much more refractory. They were compounded by mixing and blending, then heating up in the furnace until they were molten, and then quenched in water, and then ground down to fine particle size, and put in a slurry, and then either the beryllium carbide could be coated by dipping or by spraying the coating on. Then they were fired at around 2500 to 2700 in either an inert atmosphere, in some cases in air, in order to mature the coating. Even those were not particularly successful in that they tended to, with thermal cycling, crack and spall, and once you got a pinhole, blistered intensively. Beryllium oxide was also investigated, but not as intensively as the beryllium carbide because it didn't have the moderating capability. And in those days, a little bit of an aside, in those days, one of the real major concerns was the amount of U-235 that it would take to build one of these reactors. So anything that would reduce the quantity required was given priority over the other materials. But in the beryllium oxide, it was quite a bit better thermal throughput-wise than was the beryllium carbide, in that it didn't fail to around 15 to 20,000 BTU per foot per hour, a factor of 3 to 4 times better than the beryllium carbide. But the beryllium oxide powder available was not very centerable to high densities. Some small additions were tried, and one of the additions that was successful was a feldspar, and about the 1% level produced material of over 98% density. The other thing that was known at that time about the beryllium oxide was that at high temperatures it tended to be corroded by water vapor. And there was some coating work done on beryllium oxide under NEPA, but not very intensive. The coatings that were investigated were silicon metal alumina, silicon zirconium oxide, chrome alumina, zircon, and plain old aluminum oxide. And test results were very erratic, probably because of the low centerability of the BEO. The most successful systems were the silicon zirconia and the zircon. Significant improvements were resulted from recoating with the same system. The interest in the silicon addition was because of its excellent oxidation resistance up to its melting point, which is about 2600 Fahrenheit. The development of adequate coatings for BEO awaited the very intensive effort of GA&P and the availability of a more center beryllium oxide. NEPA performed design studies for both air and liquid metal cooled reactors. Graphite, beryllium carbide, graphite, and BEO plus other ceramics were evaluated for compatibility with sodium and lithium. The graphite completely disintegrated when exposed to lithium at 1350 Fahrenheit for 25 hours and was severely attacked in sodium at 1500 Fahrenheit. The high purity beryllium carbide appeared to be stable in sodium for 100 hours at 1850 F. The 70-30 mix result were similar to the graphite in both sodium and lithium. Beryllium oxide was stable in sodium up to about 2000 F for 100 hours, but lost up to about 5% of its weight in lithium at 1350 Fahrenheit in 17 hours. The NEPA project was terminated in May of 1951, and GEA&P was formed to continue the program.
When we were talking earlier about ceramic development, you mentioned that the work at NEPA continued at GEA&P through 1954 and maybe into early 55 on the fuel ceramic systems of beryllium carbide, molybdenum disilicide, and silicon carbide, as well as beryllium oxide. Then when the Air Force changed the A&P mission in March of 55, which required higher fuel element temperatures, the beryllium oxide system was best suited because of better oxidation resistance while still having acceptable moderating characteristics. Clay, could you just continue your discussion of ceramic development and focus on the years 1955 through early 1961 when the project was canceled?
Except for the event or happenings, the success of the metal fuel element and the promise of hydride moderators may have caused ceramics to fade from the scene. The first happening was that the Air Force changed the early flight demonstration to a program oriented more to development of a high-performance system. Secondly, the advanced design team, Austin Corbin, Tom Zeckley, Lou Feathers, Mel Lapides, to name a few, had been designing reactors to meet the longer range requirements. Austin, for one, was adamant that fuel element temperatures in the range of 2600 to 2750 would be required to provide a bulk air temperature to meet the long range requirements. The advanced design team was also studying unmanned nuclear powered ramjets with a desired 3000 F fuel element and a 10-hour life. When the Air Force changed the A&P mission in March of 1955, the ceramic effort immediately had some priority and visibility. Beryllium oxide was the one material which was intrinsically oxidation resistant and had acceptable moderation and was a material being considered in the advanced design studies. The fact that BEO was subject to water vapor corrosion at temperatures of interest was of concern, but was not thought to be a major problem. While beryllium oxide was oxidation resistant, none of the uranium oxides were stable throughout the operating temperature range. UO2 with a melting point above that of BEO, 4500 F, reacted with air and oxygen over the whole temperature range. A second very important factor was the non-availability of a high-purity, readily centerable BEO. The revised ceramic effort concentrated on two areas. Development of an oxidation-resistant fuel and the development of a high-purity, centerable BEO. And both of those really go together. If you don't have one or the other, or you don't have anything, you have to have them both. The Centerville BEO program was initiated by placing orders with the Brush Beryllium Company and Beryllium Corporation of America for 1,000 pounds from each company for BEO of at least 99% purity and Centerville to over 98% theoretical density at temperatures of 2,800 to 3,000 Fahrenheit. 3 general approaches were produced to develop a stable uranium fuel additive. Now let me backtrack a moment here and show you what the problem with UO2 is. UO2 has a density of about 10.95 grams per cc, but when you start heating it air, it picks up oxygen and the density actually increases. It goes up to well over 11, something like 11.1. You continue heating it, it picks up more oxygen, the density goes way down, and there's roughly a 20% volume increase in going to its highest oxide of U3O8. You continue to pick up oxygen to a higher oxide, UO3, and the UO3 is actually volatile. So if you try to operate in air with UO2, you have a big volume change which disrupts the fuel element. Secondly, you lose a lot of your fuel. The three approaches to the stable fuel. One was to look at uranium compounds, particularly the alkaline uranates. And the best ones that we found in those were calcium uranate and barium uranate, and neither one actually had the fuel retention. They did give good volume stability when incorporated in BEO. The second was to try to see if we could incorporate the UO2 into oxygen deficient systems and then develop oxidation resistance around the UO2. That didn't work either. The third was investigation of solid solutions with just about any oxide that would form a solid solution with UO2 was investigated. Ternaries modified some of these solid solutions later on to get rid of some of the problems with the binary. In total, in the course of the investigation, over 200 compositions were compounded from about mid-1955 to the termination of the project in '61. The only one really system that worked was the Yttria UO2 system. And it had two aspects of it. One, you could get a fairly high fuel content with the Yttria, and secondly, the loss and the volume stability was excellent. It would pick up oxygen when if reacted or when the tube was fired in hydrogen, but that pickup of oxygen actually led to an increased density, and you had good volume stability. Now you're going to be, in the rest of the talk, hearing about various fuel compositions, and I want to identify the codes before we go on. F48 is a mixture of 40% UO2 plus oxygen and 60% Y2O3. And the F116 has another 5% UO2 and 55 yttria. Then once the fuel additive was added to the beryllium oxide, it got a BF number with a numeral, and the numeral signified the amount of UO2 in the BEO added as whatever the fuel number was, 48 or 16. Now, if you look at the actual compositions, what was important was trying to keep the maximum amount of beryllium oxide in the system that you could. And if you take a look at 10 weight percent 116 fuel additive, you've got 89 plus volume percent of BEO in the system. If you're down lower than that, of course, your volume percentage of BEO will increase. And if you use the F48 composition, then it decreases. So for moderation and the lowest uranium investment, you wanted the highest fuel content of your system that you could get that was stable. The 48th fuel additive in this system was the F48. And that additive at 2500 F for 10 hours showed virtually no weight loss and the same result when incorporated with 6% BEO. The volume stability was excellent. The test temperature was then raised to 2750 F, and a 10-hour test had a weight loss of about 0.3%. As a result of this development, the BEO fuel element effort accelerated. While other solid solutions and modifications of solid solutions with other oxide continued to be evaluated, a major effort was implemented to gain an understanding of the UO2-Y2O3 system. Phase diagram studies at Denver Research and GE General Engineering Laboratory were initiated, and uranium vapor pressure measurements for various UO2-Y2O3 compositions were made concurrent with the progress in developing a stable fuel additive. Brush and Brilco were delivering trial lots of BEO powder. The brush material contained up to 0.5 weight percent sulfur, and the Brilco up to about 0.4 weight percent sodium. Both materials, though, were centerable to over 98% TD in the temperature range of 2750 to 3000 F. Both the sulfur and the sodium were greatly reduced during sintering, but as will be discussed later, led to fuel and sintering problems, primarily dimensional stability. Gotta have a drink. In the ceramic reactor design area, design using BEO in the form of round, thin-walled tubes and BEO moderator slabs is well along. In this time period, about mid-third quarter of '55, the effort on the ceramic core reactor was accelerating rapidly in both the design and materials activity. The decision was made to run a large test in the heater 2 facility in the large central cavity for testing the various advanced fuel element design. The 2B insert was placed on test in February of 1956. The testing has been described by Bob Evans. The mechanical integrity of the fuel tubes was excellent. However, significant BEO crystal deposits were found in some of the tube bores starting at about the end of the 4th stage, increasing through the 5th stage and part of the 6th stage, and significant decrease in the 7th last stage. As had been previously indicated, water vapor corrosion of BEO is well known, but the extent was not thought to be a significant problem. The water vapor corrosion experienced in insert 2B demonstrated this optimism to be a considerable misjudgment. Within a month's time of the discovery of the extent of corrosion in insert 2B, a chaotic effort, and I do mean chaotic effort, was underway to develop a coating to prevent the corrosion. Thermodynamic calculations to define the relationships of temperature, water vapor content, mass flow rates, and to verify controlling mechanisms were also in progress. This later effort was by Mel Lapides, Bob Spare, and Julie Malkin. Coating task forces were formed, materials personnel who had been working on metal hydride moderators, Bob Van Houten for one, and oxidation-resistant metal alloy development were put on the coating problem. No coating system was too bizarre to be studied. Whether or not the coating had high potential to degrade the temperature capability of the BEO-UO2Y203 system was a minor consideration. It's not my intent to toot my own horn, but my input from the beginning was that only two coatings should be considered. High purity aluminum oxide with at least minimum additive possible, and a hafnia-free zirconium oxide stabilized with yttrium, not calcium oxide. Calcium oxide is a common material used to stabilize zirconium oxide from crystal transformations, but it is, has a very low eutectic with the beryllium oxide. I believe it is fair to state that only these coatings were being considered after a few months. The major effort on zirconia coating was co-extrusion because of its inherent advantages. Fred White and Al Cobell were instrumental in its rapid development. The co-extrusion process was developed to the extent that uniform 3,000 to 5,000 thick coating could be applied to the ID of the fuel tube, and this coating provided corrosion protection to at least 2,650 Fahrenheit. Starting with the revitalization of the ceramic effort in mid-1955 to the third quarter of 1958, tremendous progress had been made in both the ceramic materials effort and in the reactor core design using the ceramics. A volume-stable fuel additive with acceptable fuel retention when incorporated in BEO is available. High-purity centerable BEO was also obtainable in production quantities from both Brush and Brilco. The water vapor corrosion problem appeared solved. Results from numerous reactor tests of fuel tubes were positive. Tests in the MTR and ORR showed the fuel element could operate at design power densities. While there were still many unknowns, the ceramic system BEO, BEO-UO2Y203, and ZRO2Y203 showed high potential to provide a high-performance power plant. The third quarter of 1958, the Air Force changed the nuclear-powered aircraft mission again. A part of this change was that propulsion system capable of Mach 0.8 to 0.9 with 1,000-hour life be developed. The system was also to have potential for development to higher performance. The development status and potential of both the metallic and ceramic reactor materials was extensively reviewed. Because of the potential of the ceramic system to meet the longer range performance, the BEO system was chosen for development. Results of vibration and G testing of the D10E tube and slab design had shown unacceptable displacements of core components, and a new ceramic reactor design was in hand.
Clay, that was an excellent review of the development of the yttrium stabilized zirconia ID-coated BEO-UO2 fuel element. You mentioned that you wanted to summarize the status of the D140E fuel element at the termination of A and P. You mentioned these 7 areas of interest to be summarized. Fuel stability, water vapor, corrosion, fabrication and mechanical properties, radiation effects, self-bonding, reactor testing, and fission product release. Because of time restraints, would you concentrate on just the fuel stability, water vapor corrosion, and radiation effects? Then if time permits, we can quickly give the status of the other 4 areas of interest. Clay?
This is a plot of the fuel additive system, and this is the fuel additive composition chosen for the final fuel element. It has a 45 weight percent UO2. It has the lowest fuel loss of any except at the very high yttria content. But it is a composition that maintains the most volume percent BEO that we could get into the fuel element. When you look at the vapor pressure in air of UO2, which goes to U3O8, it's up here. And if you look at these additives, this is the F48 additive, which was the first one that really showed promise. This is the F116, which is the composition of interest. If you'll notice, there's about 3+ orders of magnitude difference in vapor pressure. When you incorporate that into beryllium oxide, you get roughly another order of magnitude lower in vapor pressure of the UO3 over the U3O8. And that is the basic fuel element stability that we're going to be talking about throughout the rest of the talk. This shows fuel loss for the clad and for bare tubes. And here at 2600, we're talking about a 0.5% fuel loss for a 1,000-hour test. If you recall, in the case of the temperature distribution, there's practically nothing in terms of total quantity that was at 2600. The 2600 for the clad tubes is about in the range of a 0.5%, and for the unclad tubes in about the range of the 0.5%. One thing that I should have talked about in that design is the compressive loads on it and the hexagonal shape. There's very little flow through the high temperature portion of the reactor. There undoubtedly is some flow, but that's important both from fuel loss and from water vapor corrosion. Our assumption was that the backside of the tubes did not need to be coated to prevent fuel loss and or water vapor corrosion. In this case, the clad is only on the bore, so these fuel losses are coming from the whole tube. In the actual design, these are going to be back-to-back, and you're not going to have much fuel loss off the back. So these are maximum fuel losses that we're talking about here. This is just a plot showing the 1,000-hour test at 2,500 Fahrenheit. And this gain in weight here is not an actual fuel gain. What happens there, the tubes are fired in hydrogen. They come out in a reduced state, and then the fuel additive picks up oxygen. And if that were UO2 picking up that oxygen, then you'd have volume instability. In this case, the density actually is increasing, so you've got excellent volume stability. And that's 2,500F. This is just another one, shows the reproducibility. This particular one is at 2,800F. And there's nothing in the design that comes up into that temperature range. Now I'd like to go into the water vapor corrosion. And what this table here outlines is uncoated VEO tubes at various dew points and at various temperatures. And In these cases, you generally get crystal deposits in the tube, which results in pressure drop increases. And you'll notice here that a lot of these tubes have 10. Here's one with 34 to 41% increase in pressure drop. And that's going to not work. These are coated tubes with the and here you see practically no pressure drop. 1-2%. There's one there that's 4.5% roughly, but it shows that and these are 1,000-hour tests. They're in the range of 2,500. Here's 2,600 down here, and some of them are negative, some positive. So the coating is protecting against the water vapor corrosion. They're coated with these zirconia tubes. These numbers over here tell you that there's no really a deposit in the tube, no crystal formation in the tube. And here we've gone up again. Here's a 2800F test, 2700 test. So I think we can conclude that the water vapor corrosion has been solved. Radiation effects on the unfueled tubes are important because beryllium oxide has a hexagonal crystal structure, and in general, radiation causes hexagonal crystals to expand more in the C-axis direction than in the A. So if you get a lot of growth, then this results generally in a significant strength decrease, and the question was whether or not that radiation would decrease the strength enough and allow the loads on the design loads. Two types of damage that we are concerned with: atom displacement damage, which if you count for the particular reactor design here, here's 1,000 hours over here, and at room temperature or very low temperature, you get up here where through the course of that lifetime about 6 or 7 times 10 to the 21st of the atoms have been moved out of position. Now that doesn't mean they remain out of position, but they've been moved. Now if you up the temperature to somewhere in the range of 1800 F, then you saturate here at about 2 times 10 to the 18th displacements. The other thing that concerns us in beryllium is that when you absorb a neutron, you get 2 helium atoms. And those helium atoms can diffuse to grain boundaries, and maybe they'll diffuse out and maybe they won't. But if they get on the grain boundaries, they can seriously lower the strength. This is a plot or a table listing some radiation effects in BEO. And remember I talked about the C-axis, and if you look here, this C-axis expansion here is about 8 times what the A-axis was, and that continues throughout in the test. Also notice that here at this sample here was irradiated at 1700 F. It's about half of what it was irradiated at 700 F, and about 1/3 of what it was in the very low temperature, 200 to 300 F. And that, percentage-wise, in terms of what that expansion would cost you across the core, about 0.5%, and the core I think was 44 inches in diameter, and if all expanded like that, it would increase it by about half an inch, which Otto's design will take care of. On the density, which again is a measure of volume expansion, here at 2.8 times 10 to the 20th, we're only getting about a small percentage increase in density. This is actually about 0.2. The worst case down here for the low density is about 0.75%, and for the high density is about 0.75%, and it saturates out pretty well back in the range of 2.3 times 10 to the 20th. And those dosage was what we expected in the unfueled portion of the reactor. A lot of reactor testing was done, particularly on the fuel elements, and primarily directed toward their stability under the power-producing densities that they were going to be subjected to, and also for fission product retention. I was surprised myself when I added up the hours of tests. In the litter we had 88,000 hours, less than the other reactors, but the total hours of test for our BEO fuel elements of about 19,000 hours.
That was an excellent summary of the status of the ceramic fuel element at the end of the GEANP program. We've just been informed we have about 12 minutes left, and in that time, could you summarize the fabrication of the fuel element that we had just talked about slightly earlier?
In the fabrication, we start out with the UO2, mix the fuel additive, it's calcined, blended, etc., reacted, then mechanically ground to get a fine particle size to incorporate in the BEO. On the other side, for the coating, we start out with the mixture and go on down. We bring them down here together and we co-extrude to get the coating on the bore of the tube. Then they're centered down here, and finally they're ground and cut to a length and inspected. Let me say something about the grinding. With the tolerances that are required in the design, the straightness and the stack up in order to have closely nestled tubes, at the time that the project closed, we were just getting to the point where we might have been able to extrude a hexagonal tube, keep it straight enough and the dimensions close enough that it would not have needed grinding. I don't believe that we would have ever arrived there. I'm now in the pellet fuel business, and we've been trying for years to center to size. We still have a long way to go, so I think that for the ceramic reactor, we would have always had the grinding. And John Mundy and those people developed straddle grinding, where the grinder went down two sides of the tube at once to a real fine art. And that was the way that a lot of the mock-ups that you've seen have been produced, and all the in-pile tests were straddle ground tubes if they were hex. In the co-extrusion process, this I give a lot of credit to Fred White and Al Clavell, who really developed this process. This is the clad cylinder. You notice it's the volume of it, very small compared to the matrix. Whole thing extrudes down here, and one of the real accomplishments was this pin down here, where you see this narrow pin to down here, and then expanding the clad out against the tube wall. And that really solved the co-extrusion process and getting uniform coatings and a good bond. Let me show you some of the temperature capabilities far beyond what can be utilized. But beryllium oxide melts at about 4470, Y2O3 at 4370, and so forth. All of these temperatures are far above what we ever be able to utilize. The other problem, though, is you can't just look at the melting temperatures. You have to look at the system temperatures. And the system temperatures that we're talking about here is the BEO, the Y2O3, the zirconia, and the UO2. And in some cases, if you were to use alumina. So you're going to have liquid, some liquid in the fuel element with alumina present in the system at 2770. And in our current system, when you initially center, you're going to have liquid present at about 2870. And that may exist throughout the life of the fuel element. Very small quantities, but this is what really limits you in terms of temperature capability and not the melting points of the individual oxides. In the design, the loads that are on there, you're worried about or concerned about compressive creep. I show this chart merely to indicate some of the flexibility that you have in ceramics in decreasing or increasing certain mechanical properties. In this case, you've got a grain size here of 13 to 25 microns when it's centered at 2750. We didn't get as high a density as we normally get there. These other structures show higher grain size with higher centering temperatures. Now you can also center for a longer time and get a higher grain size. The other aspects here that was critical, and if you recall the chart where the BEO incorporating the fuel had a lower vapor pressure, if you'll notice in some of these large grains here, the fuel additive is actually completely surrounded or encased within the grain. And that's virtually the reason for that half order of magnitude decrease in fuel loss from the BEO fuel element relative to the fuel additive itself. Here's a cross section. These are zirconia ID coated tubes. Notice the rounded corner here. That's the straddle grinding. Left this little round corner, particularly if the tube was a little small. Here, this white layer is your zirconia coating to prevent the water vapor corrosion. I mentioned the effect of grain size on some of the properties. Here's a grain size down here in the range of 12 to 15, where you've got modulus of ruptures up in the 40, 50,000. As your grain size increases, your strength goes down. On the other hand, if you were worried about compressive creep, your compressive creep would be decreasing. Chart. Mentioned modulus of rupture. These tubes are centered at 2800, which is below that eutectic. If you were to center above that eutectic, what you would see is a very similar shaped curve, but it would be significantly lower. Strengths on the 2850 material somewhere down around in the 25 to 20,000 range, almost duplicating that curve. The compressive creep, which was of concern because of those radial loads, if you look at all of it over here with temperatures up to 2800, and these loads are presumably what the design, they would experience in the design. They range down here from maybe the worst case is 1.5% at 2850, which again is far above the temperature of interest. If you look at the 2950 centering temperature up here, you'll notice that the compressive creep over here is like 0.02, 0.08, 0.09, 0.23. And where you have centered at a much lower temperature, or well below the eutectic, unfortunately I don't see any here, but believe me that the compressive creep rate is quite a bit higher. In fact, there's a big change here from 2950 down to 2850, which is again below the eutectic, so that you don't get the very large grains that you get up here in the higher temperature center. Now let me summarize. While this ceramic story has been presented by me, it involves the dedicated efforts of literally hundreds of engineers, chemists, machinists, welders, draftsmen, lab techs, test groups at Oak Ridge, Idaho Falls, subcontractors, consultants from industry and academia, reproduction personnel, and last but not least, the secretaries who decoded illegible scrolls of engineers like me. And let me say this, everybody in this room is a part of this story. Each of the above made their contribution in some way to the nuclear-powered airplane. I'm not competent to judge whether or not the power produced by the ceramic reactor was capable of meeting the Air Force mission requirements, accepting that the mass flow, the bulk temperature could be produced by the overall temperature distribution in the reactor. I am confident that the beryllium U02, Y203, ZrO2, Y203, and the BEO material were capable of providing such performance. I believed it at the project termination, and I believe it today.
Hey, that was great. And thank you so very much for all that input. You've summarized an awful lot of material here in these 2 hours of tape. Thank you again.
To do this, we might substitute the water for beryllium. And in order to get the enzyme H higher and the moderator ratio higher, we would drill holes throughout the unit, and we were going to pack zirconium hydride into that system. Now, one of the reasons we were going to pack zirconium hydride into that system was because we figured that we could operate a pretty high temperature. We could operate a fairly high temperature with that beryllium uncladded, and we could operate into this area where where it didn't begin to break off, which allowed us to go somewhere up around 1,800 degrees Fahrenheit.
That's a great improvement over the liquid.
Well, it would have been a great improvement. Now, the big problem we were having at that time was, again, the zirconium hydride was ground very fine because, again, it was used as flash powders for pictures. It was used as pyrophoric materials and so on. So we had to do something. So a fellow by the name of Dick Hanel and I went up to Beverly, Massachusetts to talk with metal hydrides, because we thought if we could take, because it was so finely ground, if we could have it bit coarser particles and then a little bit other particles coming on, it's not quite as coarse, and then the very fine particles. So if we pushed it into these little holes that we have, then we would go along and we could then increase the material, the hydrogen content in each one of those holes. Now, one of the reasons why we designed, Garth designed, if you go back, George, to the original picture that we showed, what Garth did is they took the various holes which had fuel elements in, and I'll give you a point one out of these like this. If you would focus the camera on this one here, do you want to do this, Alan? Focus the camera on this. This would be the actual size that we were working on. And the fuel element, as we've seen before, would fit right in between here. I'll show you that. The fuel element would fit in like that. And now there's a little play in here because there was insulation in here, but this is approximately its size. And at that time we were thinking about that we would make these pieces about 5 inches across the flats, and so we were going to that. Now I'm going to go back a little bit. While we were at Beverly, Massachusetts, Dick Connell and I were looking over and talking with the people of how they ground their powder and so on. They took us out in the work shed where they were making zirconium hydride, and it came in. Some of it was flat, some of it was in rods, and so on. And while we were there, they were unloading a retort, and I happened to notice that it was very strange that some of this stuff, the hydride, was fairly solid, looked good, and others were all spalled and breaking up, and others were cracked very badly. So I came back, after Dick and I came back, I got to thinking about, well, why would this stuff be different? And so I talked to Jim about it, Jim McGurty.
Oh, yes.
And I said, Jim, let's do a little experiment. Why don't, can you loan me your brazing furnace? Now, Jim and some of the other fellows were using brazing. They were brazing the fuel elements. And this furnace was a hydrogen furnace. But it had a mouth on it about this big, and we could slub the material into the hot area, and we could pull it back out in the cooling area. But it also was equipped with, you could bring pure hydrogen in it. You could also cut out the hydrogen and refill it with either argon or helium. So I said to Jim, if I could use it a few days, let's try some experiments. So I went back in and I went to the shop, and they made some little rods that might go into that little insert there. And I packed them and I put them in the furnace, and but I put inert gas in it to begin with. And then the rods were heated up, and then I started cutting the argon or helium, whichever it was. In this case, it would be helium. I started cutting it down, increasing the hydrogen, and we did that for a while, and pulled the pieces out after, I suppose, 4 or 5 hours. I don't know what it was. And looked at them, and it looked like we thought there's nothing happened to them. We thought they wasn't even hydrided. But they were nice and shiny, and they're straight. And
Like a winner.
Well, we didn't know it was a winner, so we had to go get the chemist to tell us out whether we had a winner or not. And so we took it down, and they analyzed it, and sure enough, we had a good N sub H, which we couldn't really believe. So the next thing we did will be another picture coming up. We had to really sell the idea. So went down to the shops, and I found a piece of zirconium, and I had it made up in a shape like that, and put it back in and run through the same cycle. We hadn't really got the cycle right down yet, but we run through the same cycle, pulled it out, and that came out. I showed that to Calkins, and he got excited. so that started almost immediately. It became classified.
Oh, my.
And if I remember correctly, I can't remember what they classified it. There were two. One was called Lunex, and the other was Radex, and I'm not sure which is which now. Yttrium came in, and we called it one or the other. But anyway, it was classified. Now, George, the next thing they had to do, Vince wanted us to, Dr. Calkins wanted us to do an in-pile test at the MITR. Now, you should have good memories of this.
That brings up a lot of memories, Earl, because we had a very tight deadline, and I remember it was 4 o'clock in the afternoon.
But you loaded your kids in the car. We made up this rig, remember?
That's
We
right.
made up this rig with a tail on it, what was it, 20 foot long or something like that. You shoved it in your station wagon, you loaded your kids in, and you headed for Idaho.
We headed for Idaho, and we got out there with almost enough time, but we really didn't have enough time. But we had to prove to them that they're willing to put this dangerous material in their reactor. And
You're
so
right.
not only did we have to have the rig to work perfectly, and remember, and part of this is welding very thin stainless. Only Joe North could really do that real well, and
Yeah,
there were some real good craftsmen that went into this rig. But then here we are all ready to go, and you got to convince them it's safe to put in the reactor.
Yeah, well, I tell you, I remember we had a deadline. I think it was 4 o'clock.
That's right.
And we had to get it in. We met with the safety group. Well, it was imprinted in their minds that zirconium hydride was pyrophoric. Everybody knew it. It was used as flash powder in cameras and so on. So we talked and we showed them graphs, and they all looked at us, and finally the time was coming, and I was getting exasperated, and I said to one guy, I said, call up the welding department, have them to get a acetylene torch ready, and let's take this sample. We had a sample there. Let's take this sample down, and I'll play the acetylene torch on it to show you it won't explode. That set them back for a minute. So as a result, whether they didn't want to see that or not, they felt their own safety. They said, go ahead. This was very close to their time.
We might have had 30 seconds left at that point, Earl.
Yeah. So we had a real close call there. But so we got down there, and then everybody was working on it, putting it in the reactor. People were doing this, people were doing that. And then you pretty soon you came up and says, Earl, are you sure that they've got that tubes hooked up right? And I looked over and I said, George, you're right. They don't. They got the water going into the hydride.
Wow.
So you saved the day on that. But so we changed it around real quick, and they started up the reactor, and there was no explosions. We were measuring the output gases and so on. Nothing happened for the long period of time that we had it in. I think we had it in 2 or 3 weeks
Yes.
for the cycle. So that got things going. So we had all of these people working, and that was one of the things that we had in our organization that I'd like to speak about. There was no one really trying to keep anything to themselves. Once we finished the job, it went over to somebody else, and they would come in and talk to you if you wanted to, but they had their job and they did it well. And then the other people coming into manufacturing relied upon the development people, and they did their job well. And it was a good working organization, and I think that's why this organization has stayed together on our POPSI programs and all of that, because everybody worked very well together.
Very good.
Now let's go on a little bit, George. And we finished up. We started making very large pieces of zirconium. And another thing happened about this time. The people from Battelle Memorial Institute that came down, Stan Popocki, a guy by the name of Hodge, and another guy by the name of Chuck Boyd. I don't know if you recall them or not. But anyway, they came down and they had a program that they were hydriding, or not hydriding, but cladding. They thought they could clad metallic fuel elements, and that was the gist of the whole program. They wanted to come down and talk to us about cladding metallic fuel elements. And they had a little furnace about this high, and it had a tube in it that's about that big, and they were heated it up, and they would put gas pressure on it as it was heated up, and that would cause the cladding to come down on the fuel element. So they stopped in the office one day, and we were talking, and I thought, hey, this is not a bad idea. Maybe we could do this and clad it. And this is where Carl come aboard about this time, and we started working on, we had their unit, and we set some samples up. We had a contract with them. We set samples up to be tested, and then we decided to do our own job here. Now, Carl, would you like to tell us about this furnace, because you're very familiar with it?
Well, this was a furnace set up in one of our labs, And essentially it was a large muffle with a very thick wall lowered into a furnace in which we could control the temperature using the furnace, and the pressure was set up such that you would have a large surface area on the inside. We would heat the furnace up, and when it approached over 1,000 degrees Fahrenheit, we would apply over 1,000 pounds per square inch. And this would compress the cladding over the hydride, and if all went well and we had no leaks, then we would cool the furnace down and take the head off, and we would have a bonded, clad hydride.
You said no leaks. Now,
No
I
leaks.
remember one day we had a leak.
We had a lot of problems with this because we were learning, and we were very new in the pressure bonding business, and we had
right.
probably the largest setup in the U.S. at the
We
time.
did at that time.
And we started out with a retort, I think it was of 304 stainless steel. And as we heated and cooled the furnace with various runs, the inside the stainless steel started from a straight down situation, and after a while it flaked off such that it was getting narrower and narrower and narrower down at the bottom. And then when we applied the pressure, then it would, at one point in time, it would bulge out down at the bottom. And in order to get the muffle out of the furnace, we actually had to pull it out with, I think we had a forklift. And we pulled it out of the top and it almost extruded it out from the furnace to get it out. That piece of steel was very hot.
I remember one time we were working away, and I think it was Bill Negger, Bob Simmons, and probably you, and Hal Building, and we were all in there at the same time when we were pumping this thing up to 1,000 pounds, and all at once it started hissing, and we all went out the door at the same time. No one paid any attention to anybody. Yeah.
That hissing was hydrogen?
No, it was hissing. We were using inert gases.
Oh, good.
Then we moved from that furnace onto this is the more sophisticated ones that were developed then. And these were the big autoclaves. Now the difference was that this was internal heating, and outside walls were cooled. And instead of 1,000 pounds, we went up as high as 10,000 pounds. And the instrumentation will be shown on the next slide in a little bit. And I believe this is Ernie Bartel, which was one of the guys that was doing a lot of the work on that. And so this was the instrumentation that was used in this particular one. And this is how high it stayed up. But a lot of it was down in the hot part was down in the concrete, and it was surrounded by concrete. It was a concrete pit. Now we'll move on to some of the other work that we had. We were studying at that time. And this is some of the work that we did, that you particularly did on this, Carl.
Can and seal it off, leak test it, and then have it pressure bonded. And if successful, we would have not only an oxidation-resistant cladding capable of high temperature, but also we would have a good bond, a good metallurgical bond between the hydride and the external cladding.
Well, that is good.
This you can see. You can see the cladding on the outside, the brighter appearing material, and how it is bonded to the hydride itself.
Very good.
All right, now we're going to continue on. After we had this, we're going to go into some of the larger pieces that we formed, and these are extruded. And after this is pretty well proven by 1958. There's an overlap in the genealogy that we were talking about on the materials here, because some of it was going on back and forth. But in the about 1950, I'd say 55, we begin to come up with extrusions of this sort. These extrusions, this material, this is zirconium, and it was extruded. And in the links, as I said on the first one that I showed you, it was big, about this size. And They were about, they were somewhere between 36, the final was it would be cut to 36 inches, feet, 36 inches. But we were extruding them out at about 4 feet because we needed to crop off the ends of the extrusions weren't complete, but we could cut in between, we could cut off this excess material and send it back and have it remelted. So we could cut that and we got a real good extrusion, high density. So that was one of the things. Now, this has also had two purposes that I found out. And if you notice that was the, Carl, if you remember, we were having a problem when we first started out, that the inside clad was fine. You pulled a vacuum on the inside, we could get it cladded because it was expanding out into the inside diameter. But the outside, we were having a problem with because what we were getting was wrinkles. And so we decided to put some dimples in here, which went along very well because they were using those later on to put the hollows for the control rods.
Those are planned wrinkles.
Those were, well, yeah, those were planned. That was stretched. That was stretched the skin tightly over the material, and that was when you begin to come up with the other materials on that. Now we're going to go into here's one that was used in one of the heater reactors, and this was now some of the fellows were up busy and they were doing this. This was in the work that we were doing on heater 2. It was the first time that the hydride had been put into a heater, and if you'll see the stem on there where the material, where you evacuated the material and where it was pulled down. But in the heater 2, it still didn't come up. We didn't have the high pressure system at that time, and so it doesn't show as tight a skin. And that was where we used two different types of cladding, if you remember. We had about a 0.15 mil moly in there to retain hydrogen, and then we overcladded it with iron chrome aluminum.
Earl, as I remember, the heater was Heat Transfer Reactor Experiment.
That's the name
that's
of it.
HTRE. Yes.
HTRE, yeah.
This is the second session on moderator materials, and we have with us today Bob Simmons. Bob joined the AMP program in the spring of 1955 after graduating from Iowa State University at Ames, Iowa. First of all, Bob, I want to welcome you for driving through this miserable weather to get here to help us to work on the history of the AMP project.
It's my pleasure.
Over here we have Carl Bolander, a graduate from the University of Cincinnati, and Carl will be talking about some of the research and developing of the cladding material. When you joined us, Bob, in 1955, we were deeply involved in the research and development of zirconium hydride, but we were also looking for a material that could operate at higher temperatures and hold a higher hydrogen content. By 1954, the initial work had strongly indicated that yttrium and cerium were better, had a higher affinity for zirconium, a higher affinity for hydrogen and than zirconium. I'd like to take a moment here to show you a series of curves and show you what the stability of the zirconium hydride. This line here represents zirconium. It starts out at a much higher N sub H, which is the ability to hold hydrogen. But after about, when we drop down to about 1200 degrees Fahrenheit, the hydrogen content begins to slope off and gradually goes down to where upper rating to 2400 degrees, it's just practically nil. When we reached the point we were able to get some cerium, rather, first of all, we checked some calcium, and the calcium holds up very well, but drops off extremely rapidly as you get here. Now, when I say drop off, what does that mean? That means it will build a tremendous hydrogen pressure above the metal, and if it's cladded or something like that, it will cause it to, it will definitely cause it to blister. When we developed, found some cerium, We tested that, and we found out that the curve run out pretty straight out at this area, and then it began to drop off quite rapidly. We were able to get, and Bob will be discussing this just in a few seconds, we were able to get a little bit of yttrium, and when we tested that, we found out that the curve remained very flat until we reached about 2,200 degrees Fahrenheit, and then it began to slowly slope off. But even here at 2,400 degrees Fahrenheit, we still had a very high N sub H, much higher than we had for yttrium. So when we got to that point and found out that the yttrium was probably the preferable material to use, this is when Bob was with us, and being a graduate from Ames, Iowa, we then assigned him to that job. So Robert, I'm going to turn it over to you and start talking about the technology and the separation of yttrium.
Right. Well, the rare earths are 14 metallic elements which have atomic numbers 58 through 71. If you look at the periodic table, you'll notice where Earl is pointing. That's a series of 14 elements that they're known as the rare earths. There's a fascinating story about how they got their name, but I won't bother you with that. Those 14 elements form what is known as the lanthanide contraction, and it's a phenomena of the periodic table. It makes yttrium, which is atomic number 39, if you'll point that out, Earl. It's above, up in the table, 39, right next to zirconium.
Okay, I'm trying to get it right now. 39?
Yeah.
Okay, right here.
That lanthanide contraction meant that the atomic radius of those 14 elements contracted slightly through the whole series. And in so doing, it meant that yttrium had an atomic radius that fell between erbium and holmium in that series. And therefore, yttrium was quite similar to the heavy rare earths, the heavier ones. And it occurred with the rare earths in nature. In fact, from about 1794, when the first rare earths were discovered in Ytterby, Sweden, there was very little known about the individual rare earths and yttrium because of the extreme similarity in chemical characteristics. They all have a +3 valence in their chemical compounds. Extreme difficulty in separating them, requiring exhaustive fractional precipitations and crystallizations, even distillations. That was the case up until about 1944. At that time, as you all know, the atomic age dawned, and the scientists in the Manhattan Project realized that the individual rare earths had to be separated and studied, and that included yttrium, because they were born as fission products both in the bomb and in nuclear reactors. Fortunately, about this time, there was a man on the project, on the Manhattan Project, that was interested in the rare earths. He was interested in separating them. His name was Frank Spedding, and he was a professor at Iowa State College at that time. It's now called University. Frank invented an ion exchange technique that permitted the separation of the individual rare earths and yttrium. It also permitted the separation of lanthanum. I forgot to mention lanthanum. It always occurs with the rare earths also. So that was the situation up to the time that Earl was talking about, where we got our first yttrium metal. It was a little ingot, about a pound in size. and that material was hydrided, and the values of the NSABH that was shown was quite plain. It showed the advantage of yttrium hydride as a ANP moderator. It also permitted the measurement of the thermal neutron absorption cross-section, which is a value that a moderator should have a low value in that so that it does not absorb thermal neutrons. And yttrium of that purity at that time was measured around 1 to 2 barns, which was satisfactory. However, the material at that time, in 1954, was quite dirty. The microstructure had a lot of metallics. It was very poorly behaved. It had very poor behavior with respect to oxidation. It even oxidizes at room temperature. And also the workability was very bad, a lot of cracking. So at that time, GE and the Atomic Energy Commission and the Air Force came to the conclusion that they should initiate a national yttrium program. And that program was to develop production methods for yttrium and to determine its properties suitable for a moderator. I think the success of that program can be best seen in a photograph that I used in a talk at Denver in 1959, and it's shown here. It shows one of our secretaries, Marilyn Ladd. She's holding in her hand one of the little billets that was made in 1954, and she's kneeling beside 80 to 100-pound ingots of yttrium metal that was produced in Ames Lab during the period 1955 to 1960. Actually, most of those were produced in 1959. Intermediate alloy reduction method that was developed. It was better known as the sponge process. And it also gave high purity yttrium metal, which had a cross-section consistently between 1.2 and 1.4 barns. And that value was consistent with ANP moderator requirements at that time.
Just go into the Ames laboratory. When we first started out, of course, we did not have the capability at GE to do this, and so we had to search out the professionals in this particular area. And of course, we went to Ames, Iowa. And I would like you to name some of the personalities that worked hard on it, because it proved to be pretty much a complete unit within itself. And you, of course, was the liaison person tying the work in with GE and there. And we, of course, were taking the engineering information and coming up with the designs and so on that we could, and the purity of the metal. So would you dwell on the personalities of Ames?
Yes. First of all, let me say that I think that, personally, that all of the people that worked on yttrium at Ames Lab did an excellent job. And I can't mention all those names. But I will pick out the ones that I dealt with exclusively on the yttrium development. And the first one, of course, is Frank Spedding. This man was what we call the pioneer of uranium, because he developed the uranium reduction process at Ames Lab, furnished uranium for Oak Ridge purification during the Manhattan Project. And later on, as I said, he became interested in the rare earths, and all of his work as director of the Ames Laboratory was in that area for quite a considerable time. In fact, he became so well known in that field that he won the Nichols Medal for excellence in chemistry in 1952. And there's a picture of him receiving the medal that I happened to run across out of the CNE News at that time, and I wanted to save it. Frank was an excellent scientist. The next fellow that I dealt with was Jack Powell. Jack was instrumental in the development of the ethylene diamine tetraacetic acid process for ion exchange that I mentioned previously. The next guy was Norm Carlson. And Norm was the inventor of the intermediate alloy sponge process for the production of yttrium metal.
Okay, now we want to talk about the winning of the metal from the product of the oxide.
Yeah,
So we will pick that up.
I mentioned Norm Carlson. Norm, he invented this process. It was the only place that we really got a large-scale production of high-purity yttrium metal was at Ames. And this process was one in which, if you look at the flow chart that I tried to show here, I hope you can read it. It starts with, Ames started with xenotime. That's a mineral that's high in yttrium, but it's got all the rest of the rare earths in it. Remember I talked about minerals, the occurrence with all the rare earths. Well, it's treated with sulfuric acid, and that essentially digests the mineral and separates what they call a yttrium concentrate. The yttrium concentrate then was taken and loaded onto ion exchange columns, and you had an ion exchange separation of the yttrium. And now, it's not shown on there, but yttrium coming out as an ADTA complex was precipitated with oxalic acid, so it formed an oxalate. The oxalate then was fired at around 950 C to Y203. The Y203 then was converted in Fred Schmidt's rotary kiln to YF3, the fluoride. The fluoride was mixed with calcium chloride, magnesium, and calcium, and then loaded into a bomb, a retort, heated, and that's where your reduction occurred. You got reduction of by calcium, and in the presence of magnesium, you formed an alloy, about a 20% magnesium yttrium alloy. And then the calcium chloride was there as a slag promoter. In other words, the calcium fluoride that was formed as a result of the reduction was entered into the slag with the calcium chloride and could be separated then from the alloy easily. The alloy was then demagged. That means just heat it under vacuum and pull the magnesium off. That left you a sponge of yttrium metal. Now that sponge was compressed into electrodes and then consumable arc melted under a vacuum to give you those large ingots. And this is the product, the metal products of that process. That's the sponge down below. That's your pressed electrode. You can see it was welded together, goes into an arc holder. Now, what's not shown there between that little consumable electrode and that big ingot, there was a couple of things happen. They'd melt several of those small consumable electrodes into bigger ones, and then they'd mount the bigger ones and remelt those under vacuum until you finally worked up to about an 80 or 100 pound ingot. That was essentially was the Ames process, and it was producing, well, it produced 10 tons of yttrium in the period 1957-1959, and it was used also, same process, at Crane Metallurgical in Chicago, and they produced, in the latter part of the program, they produced around 9,000 pounds of yttrium. Now, I should say one thing here, that is just before the demise of A&P, Norm Carlson wasn't satisfied with the workability of even the yttrium metal produced in 1959. That is, the ability to extrude it. Because some of that material in 1959 was difficult to extrude. They had to go to 1350 Fahrenheit at Nuclear Metals to do it. So he decided he's going to make a small batch of yttrium using a variation on that process flow sheet. Principally, that was taking molten yttrium fluoride, which he already had, and stirring that magnesium yttrium alloy with it in a titanium crucible with a titanium stirrer. He got a marvelously ductile yttrium metal out of that. He got 400 pounds of it. Unfortunately, about all that happened to that was that it was sent out to Hunter Douglas in Riverside, California, and was extruded. And it was successful at 500 degrees Fahrenheit, and I think it probably would have squirted out at a lower temperature even than that.
Okay, Carl, we'll pick you up on this, on a little bit of the fabrication after this technology that we had worked out in the zirconium was transferred over to the fabrication of the yttrium hydride. So would you give us a few words on some of the things that in the transfer of the technology to making different testing and making different specimens?
We started out with small rectangular specimens shown in the middle of the photograph. In the middle of the photograph, Earl. They were quite small. We would clad them with iron chrome aluminum type alloys. We would affix a tube on the end of the can, and then have that sealed off so that the yttrium hydride was in a essence a vacuum. At that point, we would put these can yttrium hydride specimens into a pressure bonding apparatus, heated up to above 1,000 degrees and about 1,000 psi, pounds per square inch. And the bond was then formed between the outer sections of the yttrium hydride, and after it was cooled down, we would take it out of the retort, and then it would be fully pressure bonded, and the cladding was affixed, and we were able to, at that point, go on to more extensive curved shapes.
Now we'll move back to you, Bob. And well, first of all, I would like to, before I move to you, is talk about a little bit of some of the work that was put together. And out of this work, the AEC did sponsor several books. This is the one book was put out by, can you get a picture of that one? And this is one book was put out by and put together by the University of Denver, where they took the work that we did at Evendale and correlated it with all the other information on hydrides. The authors of this book was Bill Miller and Jim Blackledge, who headed up the laboratory, George Libowitz and Charlie McGee. Now, Charlie McGee was one of our own people at GEAMP, but later on transferred as an instructor at the University of Denver. And finally, I would mention Chuck London, which also did a tremendous amount of work. Bob, there was another book put together on the rare earths. Would you like to touch on bases on that one
Yes,
just a minute?
this is the book. Carl's got one. It was a book of the symposium given in 1959 in Chicago on the rare earths. And there were, I don't know, about 10 of us
At least.
that gave papers there. Carl, I think yours was on
Mechanical fabrication.
mechanical fabrication. And mine was the mechanical properties, I remember that.
There are all you young fellas there.
That's us,
That's you.
back in 1959.
I'll point them out for you. Name them off and I'll point to them.
Yeah.
This is Carl, and there's Carl there. John Lachman. This is you, Bob.
Yeah, that's me.
And we have Ray Lutter, Coy Huffine, Joe Williams,
Joe Williams.
and John Collins. And that's where that information was given, and that was the source of the book here.
That's right.
Now, what were the spin-offs, and what do you think it was accomplished out of all this work?
But starting in 1960, when we went over into nuclear materials propulsion operation, NMPO, instead of ANP, right?
Right.
And at that time, we were using Y2O3, yttrium oxide, to stabilize the high-temperature form of zirconium oxide. We were also using it to stabilize UO2 and in a BEO fuel element, which was the primary ceramic fuel element in the ceramic ANP reactor. There was a number of things that's happened through the years. For instance, in 1962, there was neodymium doped glass for highly efficient laser guides. That the guides being the tubes by which laser beams can be focused down. And they were highly efficient with neodymium in it. Coatings of lanthanum and oxide and tungsten oxide were put on to tungsten, and these behaved at high temperatures without oxidation, which is quite a feat. In the jet engine era, there was additions of cerium and lanthanum and gadolinium oxides to the nickel-based superalloys, for instance, that were used in jet engines. And they were put in there primarily to prevent what they call hot corrosion. And hot corrosion was caused by sulfides, which were always present. Now, I think the most fascinating one that I noticed as in the period of 1989 to 1988 to 89, there's a yttrium, barium, copper oxide that was formulated and found to be superconducting at about 93 degrees Kelvin. Now what that means is that this material will conduct electricity with no resistance in liquid nitrogen temperatures. Liquid nitrogen at 73 K, which means now you've got a means of using perhaps magnetic levitation to move vehicles, practically speaking, because you can use liquid nitrogen to foster it. So I think that's going to be a place where improvement is going to be coming. And it is an yttrium compound. And a fascinating yttrium use that I've noticed in the 90s. And it's rather peculiar because it concerns yttrium-90. It's an isotope. Yttrium-90 is a soft beta producer. And beta ray is a soft way of destroying a tumor. So, but the problem with that, you can inject it into the site, or you can put it in haphazard, but there's no way to target the tumor. Somebody found out that there was a way to bond monoclonal antibodies to that yttrium-90. Bind it chemically. Then when what happened is that when they put it into the tumor site, on the tumor is they have what they call an antigen that's always present on the surface. And that monoclonal antibody recognizes that antigen and it attaches to itself to it. So you see what happens? Yttrium-90, the soft beta rays are right down on the tumor, no matter whether you inject it, wherever you inject it, in that vicinity. So that, you might say that that's a real magic bullet. I think in closing, one thing I want to say, several years ago I picked up an article that said, whatever happened to the nuclear nuclear aircraft reactor? Well, the reactor is only on paper, and the HTRE3 is probably mothballed. But what we saw was a tremendous technology transfer, both, as I said, in technical information and in scientific talent, and it benefited this nation and other nations.
Well, Jim, this is one of the last sessions that we have on materials. We've gone through all the different parts of the material building of a reactor. These parts were not considered when we first started out as a high priority, but we picked them up later on. Of course, the first high priority was the fuel element, correct?
And then the moderator.
And then we followed with the moderator. Yeah. And that took a development of about a couple, 2 or 3 years.
But as it turned out, the creativity that was necessary to bring these into reality was almost as great as that for the fuel elements and moderators. The structures and configurations we have were entirely new.
Yes.
And 10 years before the project started, we just couldn't do it, because we did not have the technology to do these rather exotic things.
Yeah, I was thinking this morning as I was reading over some of this stuff, when we first started, really very little technology. And this, actually we had to explore the full periodic table, almost from one end to the other, because some of the requirements were the required light elements for neutron, thermalizing the neutron. And we went all the way up to the heavy elements to collect the gammas. And we also had to go into the rare earths to find out those elements that had high cross sections but were stable.
Mm-hmm.
So it took us quite a while to analyze, and every time we went into a new area, it had to be proven by the other group of the people that did the testing.
Yttrium was essentially unknown when we started out. And its nuclear cross-section was excellent, so with a fair amount of effort we managed to get 10 grams of yttrium, and the purpose was to see if it had any effect on stainless steel as a strengthener. And as it turned out, it had no strength whatsoever advantage. But later on we found that this was the optimal hydride. And from the finding of the yttrium hydride really made possible the high-temperature reactor. And incidentally, the AEC effort that went into providing the thousands of pounds of yttrium also had as a byproduct large amounts of the rare earth elements which were hitherto unknown, such as gadolinium and europium, which then turned out to be valuable for control rods.
And some of those are still being used today.
And they are,
Not only in control
europium
rods,
in
but
particular.
yeah, and some of the other. One of the other things that we had to do, you would think at the time we were operating with and trying to put this the fuel arms together with stainless steel, that there would have certainly been enough brazes available to use. But we found out that we couldn't use any of the common brazes.
Well, there were commercial brazes available for brazing the heat-resistant alloys, iron-based and nickel-based, but they all contained silicon. And we found after a relatively short time that the silicon content of the braze would react with the UO2 in the core and liberate elemental uranium, which could then diffuse to the surface of the cladding and provide a leakage of fission products. So we had to go ahead and develop a braze that did not have this property. And we had turned our attention to germanium, right, I'm sorry.
Well, that's all right.
Yeah,
I have little slips now.
Germanium is a member of the silicon family and has a lot of the properties of silicon. But unlike silicon, it has a low affinity for oxygen, and as a result, it is non-reactive with UO2. And additionally, the oxide of germanium is reducible by hydrogen, so that it is possible to heat treat braze structures in hydrogen without picking up any oxide, such as is the case with the silicon-containing brazes.
Yeah. No. I think we had a patent on that. I don't know. There was about
there were patents
two or
on
three
it.
patents on that.
Additionally, the strength of the germanium brazes was very good as compared to the silicon
I know
brazes.
when they were tested, we found out that the strength was quite high. So with now we had a number of other things that going into the reactor assembly that, as I said before, we really did not give these the high priority until we got ready to, and the engineers come up with a what we call the high temperature reactor, which was brought in by the fuel elements, which was brought in by the development of the zirconium hydride and the yttrium hydride, and that eliminated all the pumping and all the other things and gives a completely air-cooled reactor. So we will begin to talk about now some of the other things that we had to get into. And just for the beginning to help out, we had the front, what we call the front plug, we had the reactor, and then we had a tremendous amount of shielding going around, and then we had the rear plug. Now, one of the interesting things about it, why we wanted to get the reactor as small as we could, is because anytime we increased the diameter of this reactor, the shielding weight went up. A closer look at the wavy wall design.
In the shielding, the first objective is to moderate the neutrons down to where they can be absorbed, and then incorporate the neutron absorbent materials, typically boron, but as our work proceeded, we abandoned boron and went to some other materials. And then finally the heavy shielding to absorb gammas at the backside.
Which is sort of interesting because we went from one end of the periodic chart to the other end of the periodic chart to stop the radiation.
Well, the low end, you get the moderating effects, and the high end, you get the
moderating
absorption
effects and
effects.
so on. And then we go into, well, we have a general cutaway of the major shielding. And again, that was we went to the light elements in this case. Well, we have a general cutaway of the major shielding. And again, that was we went to the light elements in this case, which we forced it into the lithium hydride. And we went from lithium, because it was part of the lithium, this lithium-6 has the high cross-section, and the hydrogen did the moderating. So we had some absorption.
So it was a combination of moderation and absorption. Moderation by the hydrogen and absorption by the lithium.
And but in between that, between the shielding that we had this layer of beryllium for the reflector. And again, we were thinking ahead, if I remember correctly, we were thinking ahead, and if the beryllium didn't work, we came up with a zirconium barylite, which is quite brittle, but we did have that. And, we did work on it. We tested it in a reactor I remember going and testing
Yeah,
the
that was an
LITI.
advantage, and that was one of the compounds that this effort produced. But basically, I think in the end, beryllium was the material that
It was
was
the
most
easiest to work
satisfactory.
with, and the
Easiest and-
machinist
yeah.
had worked, got that down pretty good.
Yeah.
Yeah, they had that worked out. But I wanted to go into a little more into the lithium hydride now. We had to use a number of ways of trying to get this in a shielding design. And one of the, well, first of all, let's talk about the methods of that we worked. We did cold
Well,
pressing,
Cold pressing, hot
Hot
pressing, and melting.
melting.
And lithium hydride is really a very nice material. It has a very nice melting point at a relatively low temperature. And in the molten state, it does not decompose and can be held as a quiet liquid without any real trouble. The only real problem is that on cooling, there is a considerable shrinkage.
Mm-hmm.
And for that reason, special solidification processes had to be developed, essentially cooling directionally so that as the bottom went solid, the top would remain liquid and continue to feed material into the shrinking structure.
Yeah, more or less zone cooling. We
Right.
started out, we cooled it up.
Well, yeah, that is
It
on
could
cooling.
just keep
really.
it going up, and as it cooled, and then you got to the top, and then you put a pipe on it. You had a pipe,
Right.
and then you could cut it off and seal it, and that was it.
Another advantage, well, lithium hydride is reactive with the moisture content of air, so, and it is reactive with air, so it was necessary to clad it with oxidation-resistant alloys, such as stainless or nickel-based alloys. And luckily, lithium hydride is non-reactive with these metals, so you can actually melt lithium hydride in a stainless steel container without any problem whatsoever.
Which is sort of unusual because most of the hydrides particularly start degassing or losing hydrogen as they go into the melting phase.
Yes.
And again, that was a hydride that we come up with that.
Well, this is the
before
only
we-
hydride that you can melt without losing the hydrogen.
Right. And so that was a big step forward in cutting down the size of a reactor, the weight, more not the size, but the weight.
Yeah.
And then the next thing, of course, we had to do was the testing of it. And we did test it. We have one design here where it was put together and tested. I think there's a 45-inch part of the shield. We had to have it done, John. We had 45-inch part of the shield, 45, not inches, but degree. Basically 1/4 of it. And that was built by the Bud Company. Was that correct? I think it was.
Yeah.
Bud built that. They went to Oak Ridge and they did some testing there.
Mm-hmm.
And I believe Wright-Patterson did the thermal cycling on it. I'm not sure, but I think they did.
Yeah, the main problem with lithium hydride is heat is going to be developed in it, and there is a heat removal problem. There is also a high thermal conductivity, low thermal conductivity, so and thermal expansion. So there are problems of cracking. So it became important to come up with structures in which there could be a dissipation of heat and also a resolution of the problem of the structure being integral under conditions of thermal cycling. And to achieve that objective, various honeycombs and wire structures were incorporated within the lithium hydride, and these provided a means of reinforcing the structure under conditions of thermal cycling, and also were a means by which heat dissipation was no longer a problem.
That is a way of traveling out
Yeah.
to the surfaces. These systems were air-cooled, and so there was a possibility of getting the air,
Yeah.
the ram air coming in and cooling the system, so
Right.
we didn't have to require any other work. One of the last areas that we moved to, that we went through a series of things, was the control rods. And at the beginning, of course, the first test reactors that we run was primarily with boron carbide and aluminum matrix. And then as the temperatures got, like at the HTRE-1, we went to the boron carbide with the stainless steel matrix. And that was cladded with stainless steel. And then finally, as we got to the final reactors where we were getting ready to really test reactors for the actual running of a nuclear aircraft, we went to the one of the rare earths that we had come out as a product of the yttrium separation.
Well, here again, the problem was temperature. And the boron carbide aluminum matrix type of element was well known in the industry and essentially almost readily available. But unfortunately, the temperature limitations of that material are limited by the melting point of aluminum, which is relatively low. Additionally, if you remove the aluminum and go over to a stainless steel type of structure with a stainless steel cladding, you get the oxidation resistance. But here again, it turns out that boron carbide is reactive with the iron-based alloys at such temperatures. So it was really, and there are no other refractory metals of boron that could be used for this purpose. So that's when our attention was turned to the rare earth oxides that were nuclear poisons, and europium oxide in particular. And here we have a material that is stable at all temperatures to the melting point of the claddings, and it was ideal for operating to the limits of the oxidation resistance of the claddings. Being a ceramic, the problem of thermal expansion and thermal cracking was an issue, and the final product that was used was actually a 60-40 mixture of europium oxide and nickel, a ceramet type structure that resembled the fuel element, where here again the nickel is serving to stabilize the structure against thermal cracking and also providing a means for the heat to be brought to the surface for dissipation by air.
Now we studied several techniques on making this fuel element. I mean, not the fuel element, but the control rod. We did some swaging studies on it. We had a large extrusion press, and we extruded some. And finally, I think we found out the most effective way was another development we had, which was the hot isostatic gas pressure bonding. And this illustrates a little bit of one of the products was gas pressure bonded, and in between each segment of was the europium nickel mixture, and it had been sintered to a reasonably high density. And then we had little metal slots in between here, which were actually, after it was completed, they were cut, X-rayed and cut, so that they could produce little segments of fuel elements. And then these were laced together with Inconel, I believe, thin strips of Inconel, so that if the thermal, if they got hot at the thermal expansion, if it was uneven, the Inconel strips, of course, would allow it so it wouldn't hang up in the reactor. So, and this is a final picture with the poison sections in between there.
There's one little thing that I might add here, and it's really of first importance. The methods of consolidation, such as the hot gas isostatic pressing. This came into being. It was started at Patel as a laboratory type of operation, and we picked it up and essentially transformed it into a commercial application. And it turned out to be ideal for consolidating cladding and fuel elements, for making moderator components and cladding them. but also here in the control rods. It turned out to be the ideal way for joining together the cladding and the matrix so you had a continuous metallurgical structure.
Just as I've had, John Collins told me after the program was ceased and there was very few people there, the one area that was the busiest was the high temperature gas autoclaving bonding. And Joe Hopkins was doing that afterwards. I think Ernie Bartell used to do it.
Yeah.
And then Ernie left and Joe was doing it. So
There is another thing that I think is worthy of mentioning. While we did use the brazing extensively, the electron beam welding came into
effect, yes.
effect, and in the latter part of the work, it was a tool that was used routinely for accomplishing the most beautiful welds and providing structures that 10 years earlier would have been impossible to achieve.
Yeah, we could probably ask John whether or not that when the ultrasonic drilling began, was that come along too? Where
Oh, yeah.
we were using spark drilling and
The electrochemical drilling,
Yeah.
electrical discharge drilling.
and those are widely
When
used.
you're working with materials such as tungsten and tantalum and iridium, various types of ceramics and combinations of these, when this project started, there was no machine shop that could have produced these things.
That's right.
But during this period, all of these new methods of machining came into being and really contributed to the success of the effort in producing the things that had to be produced.
Yeah, I think our machine shop was on the forefront of all machining at that time. They got caught with a lot of elements that they didn't know about, and they got caught with a lot of high temperature materials that were very hard, and ceramics that had to be machined and so on.
When the GE Aircraft Nuclear Propulsion program was canceled in 1961, the US Atomic Energy Commission awarded GE a follow-on program to focus on high-temperature evaluations of nuclear materials in support of the AEC's established or planned nuclear projects, especially those associated with the liquid metal fast breeder reactor. This new program led to the name of GE ANPD being changed to GE NMPO, Nuclear Materials and Propulsion Operation, and later changed to GE NSP, Nuclear Systems Programs. In my discussion, I have selected a few mechanical property evaluations that have attracted special attention and that have been the subjects of formal publications. The first of these involves measurements of creep rupture behavior of refractory metals to 5,400 Fahrenheit. Special recognition should go to the late Pete Flagella for his very capable direction and management of this particular material study. All the metals involved in this high temperature measurement are shown in the first slide. With all these tests, they were performed in either hydrogen or argon using tungsten rod furnaces that evolved from our years of A&P experience with high temperature sources. One illustration of the type of data, before I go into that, I wanted to focus on the first slide, which shows the 4 refractory metals that were evaluated along with 3 refractory metal alloys. One example of the type of data generated is provided in the second slide, based on tests of tungsten. These stress rupture results cover the temperature range from 1600 degrees C to 3000 degrees C. That is 5400 degrees Fahrenheit. And they identify fairly parallel isotherms. If, for example, the 100-hour stress rupture strength is desired as a function of temperature, that information can be read right off this particular graph. This is a graph of stress versus rupture time. A similar plot has been prepared based on steady state creep rate. So a plot of stress versus this creep rate has been made available. Similar plots were made available for all the metals that I mentioned in a previous slide. One other very special materials evaluation involved low cycle fatigue testing of 304, 316, and 348 stainless steel in the temperature range of 800 to 1500 degrees Fahrenheit. This type of materials test was not mentioned when the GE NMPO program was first formulated by the US Atomic Energy Commission, but their extensive studies of nuclear component failures, and I might say non-nuclear component failures as well, suggested that such failures were probably due to a fatigue mechanism. As a result, GE NMPO was approached in 1964 to include this special testing in the NMPO effort with the objective of determining the best experimental procedure to use, acquiring the necessary test facilities, and of course to perform the test in sufficient detail to serve the objectives of the program. The technology of this special effort was assigned to Ray Stentz, Tom Slott, and Jim Burling. Following a detailed assessment of the available low cycle fatigue test procedures, it was decided to perform strain-controlled evaluations using push-pull loading of inductively heated hourglass-shaped specimens, and to use an elastic hinge extensometer for diametral strain measurements. This detailed assessment also led to the conclusion that the commercially available fatigue test machines, and there weren't too many of these at the time, were not capable of achieving the type of fatigue testing evaluations that were planned for this program. It was decided, therefore, to direct the NMPO efforts to the design and development of special closed-loop servo-controlled machines that were uniquely suited for low-cycle fatigue testing. At this point, I wanted to show a slide that exhibits the hourglass-shaped specimen that was employed with the diametral extensometer in place. This extensometer is positioned at the minimum diameter point of the specimen. And that diameter, by the way, was 0.25 inches for the most part. Diameters above and below that were evaluated, but the general test procedure involved the 1/4 inch diameter specimen. This is the elastic hinge here, and any displacement here, which is caused by loading. For example, if you load in tension, the diameter decreases, and then when you reverse the load and go into compression, the diameter increases. The amount of change of the diameter divided by the diameter itself gives the value for the strain. This value of strain is picked up electronically at the end of the elastic hinge extensometer, which is 6 inches beyond the hinge itself, and that's fed into the control system, which we'll talk about later, and allows the system to keep repeating the amount of strain that was set for the particular test. In preparing for a test at elevated temperatures, before you could put the specimen on test, we would put an induction coil to surround the specimen. We would slip that coil right down over the specimen and then instrument the specimen with a chromomalleable thermocouple right near the minimum diameter point, and then the specimen would be ready for insertion into the test machine. I wanted to list a few of the problem areas that had to be solved before an adequate test machine and a reliable test machine could be put on test. I've had some lines here to divide the thing into 3 different parts, and as we'll see later, each induction or each fatigue machine had 3 particular parts. One was the induction heating system and the thermocouple attachment I've already mentioned. And then the second part contained the holding fixture, the specimen holding fixture, the load frame, and the hydraulic actuator. This provided the cyclic push-pull loading to the specimen. And then the third part of the fatigue machine is the control console. This controls the temperature to the set limit. It controls the rate of cycling. Usually that was 20 cycles a minute. It controls the strain range that was imposed, and it controls the cyclic shape. And all the data recording system, all the data recording equipment is part of the control console. This gives load readouts, strain readouts, etc. Once these problems were solved, the systems were built in-house and proved to possess the reliability desired. This was a major development for this program. Another major development involved the conception, design, and fabrication of the analog strain computer. This device accepted instantaneous signals of the diametral strain and the axial load, and in conjunction with elastic modulus and Poisson's ratio values, provided an instantaneous computed value for the axial strain component. Thus, for isotropic materials, a method was provided to allow low cycle fatigue tests to be performed in computed axial strain control when a diametral strain measurement was being made. This had never been done before at elevated temperatures. This strain computer was described extensively in an issue of the Journal of the American Society of Testing and Materials, and was viewed as such a valuable contribution to the fatigue testing field that it won the 1971 ASTM Templin Award for the authors Tom Slott, Ray Stentz, and Jim Burling. A final slide shows an example of the type of fatigue data generated in this program. This is a plot of the total strain range, and it's plotted against the cycles to failure. All the data for the 3 different stainless steels are combined on one plot to illustrate at least one point. These are the data at 800 Fahrenheit, 430 centigrade, and these are the data at 1500 Fahrenheit, 816 centigrade. The magnitude of the temperature effect there is very prominent. As a matter of fact, it amounts to a factor of 20 from the low to the high temperature. About 15 of the fatigue machines developed on this program were built in-house to serve the requests for additional data of this type. Some of these machines were assigned to the radiation effects program that we'll be hearing about a little bit later. We are now going to continue our discussion of low cycle fatigue in a visit to the Martest Incorporated Fatigue Laboratory. After GENMPO and GENSP were canceled, several engineers associated with the fatigue testing effort formed a company called Martest Incorporated to provide fatigue testing services to various customers. This company now has some 50 fatigue machines in operation. To complete our coverage of the low cycle fatigue project, I'm going to turn the discussion over now to Ray Stentz. Ray, welcome to the project.
Thank you, Joe.
Ray was involved with this fatigue project since 1964 and is the inventor of the analog strain computer that I spoke about
earlier in my presentation. Ray is one of the engineers who left GE to form a private fatigue testing company, and he's going to review in general terms the features of the low cycle fatigue machine. Ray?
Specially designed machines have been developed to subject materials to low cycle fatigue exposures. This is a typical low cycle fatigue machine. It consists of an induction generator, a load frame. The load frame applies the forces to the specimen, and a control console which accepts the signals from the load frame and controls the strain and the temperature. I'm going to cut. We'll move in and so we can get these things a little closer. Yeah, that's all right. Okay. Can you see this coil here? Okay. Okay. The induction generator supplies high-frequency electrical currents through a copper coil which surrounds the specimen. This in turn induces currents in the specimen which heats it to the desired temperature. Now the load frame is the device which originally secures the specimen at the top. It's connected to this platen. The bottom of the specimen is connected to a hydraulic actuator which moves up and down to supply the strains and the forces to the specimen. It also contains the instrumentation so that we can measure the temperature, we can determine the force on the specimen, and we can determine the strain in the specimen by putting an extensometer on the gauge length of the specimen. The control console, which is this device, accepts the signals from the load frame, from the instrumentation. It compares these signals constantly with what's required, and it makes corrections as necessary by sending electrical signals to the load frame and to the induction generator. This particular load frame in a strain control test would constantly control the strain amplitude throughout the test until the specimen breaks and separates into two pieces. The number of cycles required to do this is a measure of the fatigue life of the specimen. This particular fatigue life is consistent with only the temperature that we ran the test at, the strain range we used, and the frequency of loading. Other useful information is also obtained beside the fatigue life. The instrumentation provides a record of the material response. This is used by material engineers and designers to determine the cyclic, elastic, and plastic response of the material and the forces required to maintain the strain range throughout the test. This information eventually goes to a database which is used to predict low cycle fatigue behavior of actual components. That's all. Now, we can get an actual setup of the machine that's running, and we can put it on your shoulder. Okay. Yeah, it's probably more consistent.
Okay, Ray, we're off and running. Yeah, I think.
Alan, want to check it?
Yeah, he checked it, yeah.
Go ahead, Ray.
This is an actual fatigue test in operation. As you can see, the extensometer is coming in from the right on the specimen. The specimen is encircled with the induction coil, and the actuator is going up and down to impart the strain on the specimen. The motion is very small, and you probably can't see that. If we switch over to the console.
Okay, just a minute, we'll back that up.
Okay, that's good. Okay, can you see this part here?
Yeah.
Okay.
I'm going to kill it. Yeah. Okay.
This needle moving indicates that an instantaneous correction has taken place, controlling the strain on the specimen. This recorder indicates the force and the strain that's present on the specimen. Every cycle is recorded. In addition to this, we periodically record what we refer to as hysteresis loops, which was a measure of the strain and the force in each cycle. These numbers indicate the cycle at which that recording has taken place.
Really. Well, now that we've finished talking about the high temperature mechanical property evaluations, I'm going to turn the discussion over now to Alan Feith, who was in charge of our high temperature property study that dealt with the physical properties of metals and ceramics. So now I'd like to introduce Alan Feith. Alan?
Thank you, Joe. In the aircraft nuclear propulsors were in the range for which most of the properties were known or readily obtainable with existing equipment. The lower power requirements of the reactor allowed the use of aluminum and alloy steels for structural elements. After the termination of the ANPD project, the Atomic Energy Commission requested that we determine the thermophysical and mechanical properties of materials which could be used in advanced reactors operating at considerably higher temperatures. This led us to the development of equipment and methods to accomplish these tasks. In some cases, we measured properties of materials at or near the melting point. In essence, we built upon the earlier work and extended the knowledge of material properties. Most of the studies were presented at technical conferences and published in journals. It was our good fortune that we had access to furnaces which could operate at the temperatures of interest. Our job was to develop experimental methods which could be adapted to these furnaces. We also had to be aware of peculiar things which could happen at high temperatures. Our specimens, as well as the tungsten heating element of the furnace, had to be protected from oxidation by use of very dry inert gas, such as helium. The specific properties which we measured were thermal conductivity, enthalpy, thermal expansion, electrical resistivity, and thermal diffusivity. My co-workers were Ray Hine, Art Loskamp, and the late Mike Finsel, as well as Carol Johnstone. The furnace used for thermal conductivity, electrical resistivity, and thermal expansion was a tungsten tube furnace shown in the figure here. The tungsten tube furnace is here. This particular picture has the apparatus for thermal conductivity, which was a radial heat flow apparatus. The furnace was brought up to temperature, held at a steady state, and then the centered heater was energized to provide a thermal gradient in the specimen. The concept was simple. We had to design the specimen, thermal guards to keep the center specimen isolated, and the center heater. The most difficult thing was measuring temperatures to a degree of accuracy required. In our work, we actually measured thermal conductivity of ceramics, which were very low, and metals, which were considerably higher, a ratio about 50 to 1 from the high thermal conductivity to the lower thermal conductivity. In the next picture, I want to show a few examples of the things which we were measured. We measured beryllium oxide from 1,000 to 200 degrees centigrade, or 2,200 degrees centigrade, and yttria from 1,000 to 2,400 degrees centigrade. Next slide. Molybdenum was one of the higher conductivity materials and required that we measured thermal gradients to the 100th of a degree centigrade. We also experimented in measuring tungsten with different volume percents of uranium dioxide. You will notice that uranium dioxide has a very low thermal conductivity compared to tungsten, and these are various percentages of UO2. In addition to measuring the properties, our customers required that we understand the reasons for the behavior of the material and its effect on a property. For instance, heat is conducted through solid materials by several mechanisms. One of the components is the lattice conductivity, which is similar to the travel of sound through solids and moves at the speed of sound in the particular material. Heat also is carried by electrons, so the presence of resistance of the material has some effect on the total conductivity. Some material studies are dielectric, insulators at normal temperatures and conductors at elevated temperatures. This also has a bearing. Thermal radiation contributes as well. Transparency can change with temperature, and heat can be radiated across pores in materials whose density is lower than theoretical. Hence, a correction for porosity needs to be applied. It has been observed that phase changes affect the flow of electrons and the electrical resistivity and thermal conductivity as well. Fitting property data to mathematical equations was another requirement. In many cases, power series equations could be used. However, in the case of thermal conductivity, some of the components were exponential in nature, and the power series could not be used. At the time of this work, that proved to be a challenge to the most studious computer analysts available. Data from these studies and those discussed below were published and disseminated at various conferences. The next property I want to discuss briefly is enthalpy. And in the picture shown now, we show the apparatus. The specimen was heated in a tungsten rod furnace contained in a capsule. When it reached the proper temperature of study, the container's specimen was dropped into a calorimeter. The temperature rise of the calorimeter then determined the heat capacity or enthalpy of the material in study. Next. Several pictures now are shown of the enthalpy of these materials. The picture before us now is that of unalloyed tantalum. We measured that from 1,000 degrees centigrade to just under 2,400 degrees centigrade. We are now looking at a tantalum 10 tungsten alloy. You'll see it's still linear and there's not much change in enthalpy. And here we have two other materials which are also tantalum alloys. Again, the significance of displaying these pictures is the fact that we were able to make these measurements over temperatures from 1,000 degrees centigrade to 2,400 degrees centigrade. Next. We show here that when we do an alloy material, we can also calculate by a weight percentage the enthalpy of alloys from the known values for the elements. This was molybdenum and rhenium. We turn now to the measurement of thermal expansion. The furnace used was similar to that used in thermal conductivity, and we adapted a specimen holder and parallel telescopes to read the change in length of the specimen as it was heated. Again, we had to attain the constant temperature to allow us to make the measurement of the length with the parallel telescopes. We're now going to show several slides of the materials that were measured. We measured many metals. In our thermal expansion studies, we looked at the alloys of rhenium and tungsten. The chart before us now shows the thermal expansion of rhenium, tungsten 25%, rhenium, and tungsten below it. Measuring electrical resistivity, we used a 4-probe method. We did this on numerous materials. The equipment was the same as for thermal conductivity. We used the specimen was used in place of the center heater. And this is a schematic of the apparatus used and the specimen here. It was a rather simple specimen to use and still required high precision in measurements. Typical of our measurements of electrical resistivity is that shown here for molybdenum. Okay. The last property I want to talk about is thermal diffusivity. The thermal diffusivity is a rate of heat passing through a solid material. We could do this with very small specimens. The specimen used in this particular apparatus was less than the size of a dime. We used a laser to give us a very rapid heat rise on one side of the surface, and then watched the effect of that with an infrared detector on the opposite side. This temperature rise was recorded on an oscilloscope and photographed. Analysis of the photograph allowed us to determine the thermal diffusivity. The fact that we could do this on a very small sample allowed us to use that method for determining the effects of radiation on various materials. Unfortunately, we do not have pictures of the apparatus, nor do we have data to demonstrate. The work in measuring these several properties extended the knowledge of thermophysical properties at that time, and probably has been useful in many applications.
My discussion represents a review of the GE NMPO radiation effects project that was directed by the late John Moteff. Radiation effects are actually changes in the internal structure of materials that occur once they are exposed in a nuclear reactor to high levels of neutron radiation. These changes have led to the term radiation damage because of the detrimental effects on mechanical properties as well as physical and electrical properties that have been observed. A serious loss of ductility, termed radiation embrittlement, has been cited as a principal problem area. In John's project, he organized a detailed approach to evaluating radiation effects on potential metals and alloys for use as fuel cladding materials in the LMFBR. the liquid metal fast breeder reactor. His plans were to not only measure the magnitude of the radiation effects on properties, but also to employ metallography and electron microscopy to aid in explaining just why these changes were taking place. His principal investigators on this effort were Fred Kingsbury, Joe Beeler, Bob Rau, and the late Jack Smith. In one of John's reports, he listed atom displacements and transmutations as the two processes by which crystalline solids are damaged by the neutron bombardment. And this type of neutron bombardment, as we know, is present in all reactor environments. Talking about atom displacements for the moment, I've pictured here a simple body-centered cubic structure which is typical of tungsten, molybdenum, tantalum, and several other refractory metals, with an atom at each corner of the cube and one atom positioned in the very center of the cube. In response to the neutron damage, several important things can occur. For example, if we pick this atom of tungsten, for example, and it is involved in an elastic collision with a fast neutron, it can either strain the position of that atom, or it can knock it right out of that position and have it located in an interstitial position. This creates a vacancy here in the lattice. So when we talk about atom displacements, that's the kind of collision that we're talking about. And it can either strain the lattice or it can produce a vacancy which has an effect on the mechanical properties. The next slide is a brief discussion of transmutations. And I've picked the boron transmutation, which is an N-alpha reaction, so that when a neutron is absorbed by the boron atom, this is the symbol for the neutron, it emits an alpha particle, and the boron splits into a lithium-7 atom, and it gives off a helium particle. Another transmutation, which will come up in subsequent discussion, is when a tungsten atom undergoes an N-gamma reaction. It is converted from tungsten 187 to tungsten 188, and that changes to rhenium in a certain period of time, and eventually that changes to osmium. Now all these are 188s up here to indicate that nothing happens to the atomic weight. So they're the two reactions we'll be hearing about in subsequent discussions. Now the next slide is to give some indication of just how extensive John's program was. He studied all these materials, all these refractory metals and these refractory metal alloys, and he studied quite a few nickel-based alloys. This A286 is a austenitic stainless, Inconel 800, and a couple of stainless steels, and another nickel alloy, Inconel 625. The next slide indicates another facet of the program, because the general theory then was that you can't measure radiation damage effects by measurement of just one property after the irradiation, and you should include at least four. Well, John included stress, rupture, and creep, tensile tests, electrical resistivity, hot hardness, low cycle fatigue, substructure studies, and damage calculations. And prior to the program, prior to the radiation program, all these materials were accumulated. All the necessary test specimens were machined, and then they were all sent in various groups to be exposed to the neutron radiations, either in the Oak Ridge reactor or the engineering test reactor in Idaho. And the range of the fast neutron fluences that was used went from 5.9 times 10 to the 17th to 1.4 times 10 to the 21st NVT. This is an expression of the neutron density within the reactor. The radiation temperatures, and this, by the way, has an important influence on just how the materials behave after irradiation. It's the temperature at which they're exposed to the neutrons. The temperature range was from reactor ambient, which is just about room temperature, to 1300 degrees C. And now I would like to show a few graphs depicting several interesting behavior patterns reported in John's program. This first graph is based on stress rupture data for A286, tested at 1350 degrees Fahrenheit in the irradiated and unirradiated condition. These are the results for unirradiated material tested at 1350 degrees Fahrenheit. This chart gives the stress in kilograms per square millimeter and the rupture time in hours along the abscissa. Notice the drastic reduction in the rupture life when exposed to 2.5 times 10 to the 19th neutrons per square centimeter. This is a typical behavior pattern that has been reported for these kinds of materials. Notice now the reverse effect as we see here for an exposure to 8 times 10 to the 19th neutrons per square centimeter. This is for tungsten tested at 2000 degrees Fahrenheit. And the important observation that was made is that for the unirradiated material, the stress rupture behavior is given by this line. And for the irradiation to 8 times 10 to the 19th neutrons per square centimeter, the rupture life is increased substantially. John stated his belief that transmutation products enhance the mechanical properties of the refractory metals by a solution hardening mechanism. In this case, tungsten transmutes to rhenium, and parts per million quantities of rhenium that are formed go into solution to strengthen the material. And finally, I wanted to show an illustration of the effect of irradiation temperature on mechanical behavior. You remember I said earlier that the temperature at which the irradiation is performed has an important effect on the properties. This observation is shown here where the unirradiated material has a creep response. This is percent elongation as a function of time. So this is a creep curve of unirradiated material. All tests, by the way, are of molybdenum tested at 750 degrees C at a stress of 18 kilograms per square millimeter. When exposed to 1.6 times 10 to the 20th at room temperature, the creep curve increases noticeably, but not significantly. When the irradiation temperature is increased to 700 degrees C and 1,000 degrees C, the increase in the creep strength is quite substantial. I am now going to turn the discussion over to Bob Rau, who was in charge of the electron microscope laboratory in Building D and worked extensively on the radiation effects program. Bob?
Yeah, I would like to talk a little bit about some of our electron microscopy studies that we did on irradiated materials. And maybe first I should explain a little bit about what an electron microscope is. In a way, it's similar to an optical microscope, a typical light microscope, except instead of using optical light, we use electrons, a beam of electrons, and we focus them with electromagnetic coils instead of glass lenses. The short wavelength of the electrons allows us to magnify things to much higher magnifications than we can with a light microscope. It also allows us to image much, much smaller detail than we can see with a light microscope. To do studies on irradiated materials, irradiated metals, refractory metals in particular, which I'm going to talk about, you first have to prepare the sample so that it is transparent to the beam of electrons. This means we must have a very, very thin metal section. So in order to do that, we first slice or saw a very thin wafer from the specimen, and then we electrochemically thin it until a small hole breaks through. At that point, we have a specimen which is transparent to the electron beam, and we put that in the electron microscope and scan the region around the hole where it is vanishingly thin. That is the electron transparent region. So now, to give a few examples of some of the work that we did under the program, we studied refractory metals, and in particular I'm going to start off with tungsten. I have a series of diagrams here, a series of pictures showing irradiation damage to tungsten metal. The first picture on the left-hand side shows a rather featureless background of unirradiated material. This would be the normal tungsten prior to irradiation. You can see a few dislocation tangles, a dislocation network coming down through here. Dislocations are really not anything on an atomic scale, but they are due to a misalignment of atoms in the crystal lattice. Most solid materials, metals, ceramics, and so forth, have the atoms arranged in a regular crystallographic arrangement. It might be cubic, hexagonal, something like that. When those blocks are slightly misaligned with respect to each other, the disalignment boundary then is a dislocation. It's a region where there's a slight strain in the lattice, and therefore we see an image in the electron microscope, which we call a dislocation. So that's what these boundaries are, or these tangles of dislocations are that you see here. This would be called a subgrain boundary. In the next picture, we see an example of tungsten which has been irradiated to a low neutron dosage. Again, we see some of these dislocation tangles indicative of the subgrain boundaries, but we see a lot of tiny black spots superimposed in the matrix. Formerly there was nothing there. Now we're seeing many, many tiny black dots. These are diffraction contrast images of defect areas caused by either interstitial atoms, which have been knocked out of their normal site and have now lodged in between the regular positions, or vacancies left behind when the atoms were knocked out of their original site. You can imagine this occurring when you put an extra atom into the lattice, or maybe an extra marble in a pile of glass marbles. The lattice has to stretch, it has to give, it has to expand to accommodate that. So you have distortion there. Likewise, the site from which the atom was knocked out collapses a little bit. You also get distortion there. So we can have two different kinds of defects caused by bombarding with neutrons, radiation damage. They can be interstitial atoms, or they can be vacancies left behind. And the little black dots that we're seeing here are the visible image of those defects, those radiation-produced defect clusters. Finally, on the right-hand side, in the third picture, we see a piece of tungsten which has been irradiated to a high neutron dose, and the damage is extreme. The small black dots have now coalesced into much larger black dots. In some cases, we can even see the beginnings of little loops forming where they have coalesced into larger clusters. Again, at this point, we don't know whether they are vacancy clusters or interstitial clusters, although we can do experiments in the electron microscope to determine whether they are vacancy or interstitial in nature. You can imagine that clusters like this in a metal then have the effect of creating barriers to movement of grain boundaries or subgrain boundaries or dislocations that occurs when a metal is stressed or put under some kind of a strain or tested. This hardens the metal and causes embrittlement, which of course is a detrimental factor. So in the next picture, we're going to see what happens when we anneal these radiation-damaged structures. Now we have a picture where we have annealed a piece of tungsten which had been irradiated to a high neutron dosage. It formerly had many of these black dot defect clusters in it. Now we see that we have pretty well cleaned up the background. We don't see much there, but instead we're seeing some very large, well-defined loops. In this case, they happen to be labeled A, B, C, and D because they are lying on 4 distinct crystallographic planes in the tungsten lattice, the cubic lattice of the tungsten material. The drawing up in the right-hand corner is an attempt to show those 4 planes. It doesn't show up too well in a flat perspective like this, but those loops are actually lying on 4 planes within the tungsten specimen. By doing these rather sophisticated tilting and diffraction contrast experiments in the electron microscope, we were able to determine that these are planes of vacancies, not interstitials. This occurs because vacancies are less mobile in the lattice than interstitials. When an irradiated specimen like this is annealed, heated to a high temperature, the interstitials tend to migrate out to the grain boundaries and disappear, or if they run into a vacancy, the two are mutually annihilated. But the net result is you wind up with excess vacancies, and these vacancies then tend to cluster into the loops that we see here. Lattice forces cause them to coalesce into planar loops which lie on these single crystallographic planes. To visualize it, you can think of maybe taking a stack of papers and cutting a circle out of one and stacking them back together again. The lattice is then going to collapse around that vacancy loop. So that's what we see in those cases. I don't have a good picture to show, but if we further do experiments on refractory metals like tungsten and molybdenum at high temperature, where the irradiation is actually carried out at high temperature, then we actually saw these vacancy loops coalescing into vacancy clusters or bubbles, almost look like bubbles in the microstructure. Those too act as barriers to dislocation motion during working of the metal and cause hardening of the material. Finally, I'd like to finish up with a little discussion of kind of a special project that we did studying some single crystal vanadium. In this case, we started with vanadium rods, which had been specially grown in a favored orientation, so we knew what we were dealing with going into the electron microscope. These were irradiated, then slices were taken, and our little specimens prepared for the electron microscope. And the accompanying diagram now shows what we saw when we put these into the electron microscope. This is a composite picture showing 2 electron micrographs. It shows a diffraction pattern, the electron diffraction pattern up in the top, and a drawing down in the bottom. First, if we talk about the 2 electron micrographs on the top, we can see first of all this bullseye over here very plainly showing up, kind of a white center, a darkened inner circle, and finally a larger outer circle. That is actually a cross-section of a damaged shell. We also see in the same diagram, coming down diagonally across, a series or an envelope of damage, a dark inner region, a slightly lighter outer region. And I should mention that the matrix itself is surrounded by these black dot defect clusters that we talked about before. So there's damage throughout. We have enhanced damage in these shell regions. The left-hand picture shows a very good example of a transverse section of a damaged shell where we have a core running down through the center, an inner damaged shell, which is very heavily damaged, highly populated with black dots, an outer shell, which is, again, highly damaged, but not as high as the inner shell, and finally the matrix on the outside. What this really consists of can be shown in the diagram down here at the bottom, where we see that we discovered that in this vanadium metal, this single crystal vanadium material we were working with, were occasional impurity fibers of vanadium boride. And boron is an interesting material when you put it in a nuclear reactor because it will absorb a neutron and become unstable, and then it will undergo a transmutation reaction. It will actually split because it's unstable and throw out an alpha particle and a lithium ion. That's what's going on here. We are bombarding this little vanadium boride core with neutrons. It then absorbs the neutron, it becomes unstable, it splits, and the ejected lithium ions have a certain range, a rather short range. They go out and cause damage along the way, which causes this inner damaged shell. The alpha particles, or helium ions, can travel a little farther. They create damage to a larger distance, as you can see in the outer shell here. So we're actually seeing a cylindrical damaged shell which surrounds these tiny, thin vanadium boride fibers which were embedded in there. On later annealing, I don't have a picture to show, but on later annealing of these structures, we were able to see lithium vanadate crystals located in the inner shell and helium bubbles located in the outer shell, just what you would predict from this transmutation reaction. Finally, one of these micrographs was used as the cover of an article in the Journal of Applied Physics. The article appeared in the journal, and they actually chose one of our electron micrographs to be the cover photo, which was kind of a unique experience for us. Thank you very much.
I'd like to introduce Jim to the group, and he will be part of this section on the analytical chemistry. Good afternoon, Jim.
Good afternoon.
Would you explain to me who this gentleman is on in the picture here?
Well, I was taken just a few years ago, actually about 40 years ago, and that's me when I was much younger and didn't have the color hair I have today, which I now dye to befit my age.
Or you've dyed to fit your age.
Of course.
It is actually black. I may learn that, but I need something to put on top.
Ronald Reagan and I have the same genes.
Okay. All right. Jim, in the analytical group, I know it was a fairly large group, but who are some of the members that you can recall right now? Not over, just so much we don't want to overlook anyone, but you had such a large group, I'm sure that you can, let's recall some.
Well, I joined the group in 1956 when Al Rebo was in charge. At that time, we had a number of different laboratories. Dick Kupel ran the spectrographic laboratory. Al Schaefer ran the inorganic wet laboratory. Bob Stewart was in charge of the radiochemistry laboratory, and I was in charge of the analytical research group. There were also Ruth Menke, Warren Davis, Alex Rosenberg, Bob Williams, and a number of other people.
All right. I have another picture on to begin the next part of your discussion. I have another picture on to start us out. Would you explain this particular picture here?
This is a picture of Alex Rosenberg and myself. That instrument that Alex is operating is a gas chromatograph. It was an instrument that we developed for the determination of impurities in neon. When we were given the job of analyzing neon, I went around and looked at the commercial instrumentation that was available, and the best instrumentation available had a sensitivity of only about 100 parts per million. And our job was to develop a technique capable of measuring impurities at a part per billion, which we were able to do. This is the instrument, made up of a number of commercial components, and we used amplifiers, flow controllers, and things of that nature. And we received the General Electric Technical Excellence Award for that development.
All right. You had that development, and there were a number of other analytical techniques at which you worked on, which I think deserves to be mentioned, and I will put the ones that have been identified, and I'd like for you to enlarge on those and explain each right now.
One of the problems that people in the ceramics group were having was that when they made a fuel element, a uranium oxide fuel element, at high temperatures, the uranium oxide would volatilize and result in a substoichiometric uranium dioxide, which, although stable at high temperature, when it cooled to room temperature, dissociated into uranium oxide and uranium metal. When this was clad and put in a reactor, the uranium metal would migrate along the grain boundaries, react with the cladding, and cause the cladding to rupture. And our job was to determine the amount of free uranium metal in these fuel element cores, and eventually, when they made them out of uranium oxide and thorium oxide, to determine both uranium and thorium. None of the conventional methods...
This is item 3?
No, this is item 2.
Item 2.
None of the conventional methods would work because the determination of a few parts per million of uranium in a matrix that had as much as 85% uranium, you couldn't measure uranium and tell the difference. So the technique that we came up with was to expose the fuel element in hydrogen. The hydrogen would migrate along the grain boundaries, react with uranium, form uranium hydride, then evacuate this system, heat the hydride up, it would dissociate, and then we would measure the hydrogen on a chromatograph. And because uranium and thorium would form hydrides at the same temperature, but they would dissociate at different temperatures, we were able to separately determine uranium and thorium metals in the fuel element cores. Oxygen to uranium ratios, this came about because they were having a great deal of difficulty measuring the thermal conductivity of oxygen to uranium oxide samples that were manufactured in different atomic energy installations. And this is caused by the fact that the technique used was to oxidize uranium dioxide to U3O8 and then make a calculation which would give you the initial uranium to oxygen ratio. However, the work that I had done previously in Oak Ridge taught me that U3O8 was really an accident, that the uranium oxygen ratio was dependent upon a number of things, such as the previous history of the uranium oxide, that is, whether it had been made from a precipitation with ammonia, whether it had been made from hydrolysis of the fluoride. It depended upon the vapor pressure of the oxygen, such that actually the atmospheric pressure would have an effect on the final uranium ratio, uranium to oxygen ratio. And also we're talking about item 3.
Mm-hmm.
Also the length of time and the temperature and all of these things, and so therefore people at different installations around the country were getting different results. Now, these results, under normal circumstances, would have been quite satisfactory because they were within the limits of accuracy that one would expect. However, since the values were not correlating, that is, the thermal conductivity values were not correlating, we had to determine something that was more accurate. And so the method we chose was to dissolve the uranium and then convert it, the solution, the uranium in solution, convert it back to an oxide by evaporating the acid, evaporating the rest of the liquid, and then igniting it under a preset set of conditions. In this way, we destroyed the history. The uranium in the solution didn't know where it came from. Now, for scientists like you, of course, you know that the blue ones would come from the precipitation with ammonia, and the red ones would come from if it had been precipitated as the fluoride.
No, that's very enlightening, Jim.
Well, I mean, scientists really learned to know the best way of distinguishing
Sure,
some of the
sure.
atoms and the atomic species
Right.
is by the color of the atoms.
Right. You want to move on to 4 then?
The application of the double withdrawal countercurrent extraction technique to analytical chemistry. This came about when I went to a meeting in New York, and I heard a fellow by the name of Craig discuss the use of the double withdrawal technique to separation of materials that were very difficult to separate by extraction. And after the meeting was over, I asked him if anybody had ever tried to do this analytically, because it seemed like an excellent technique to determine elements that were very difficult to separate. And really the foundation of chemical analysis is separation, because when things are in solution by themselves, if you have a pure material, it's relatively easy to analyze them. It's the main problem is to separate things from other elements that would cause interference with your measurement technique. Well, I set about trying to do this, and it turned out to be a very interesting mathematical problem, and was able to develop some mathematics that allowed us to predict how this thing might work. And we actually used it to separate a couple of elements, tungsten and molybdenum, and we theorized that it could have been used to separate neighboring rare earths, which at that time was an extremely difficult problem. The only way I know that it had been done at that time was by spreading out at Ames, Iowa.
Mm-hmm.
And that paper turned out had very little application to the fuel element work, but I got more requests for that paper than anything else I had ever published. Requests came from all over the world because they were interested in it as an analytical application for the determination of things that were very similar chemically.
Mm-hmm. All right. You had some other interesting work that you did on item 5. Would you briefly touch on that then?
Well, as an analytical chemist, you find that depending upon what material that the people are working on around you, for example, yttrium oxide, as you remember, we did a lot of work on that. You develop methods for determining a bunch of elements in yttrium oxide, and then 6 months later they're interested in something else, say beryllium oxide, and so you develop the same methods over and over again. And it finally seemed to me that maybe we ought to have a method that would allow you to determine an element regardless of the matrix. And I set about trying to do this and ended up with quite a bit of success. And as a test of it, Dr. Lewis Garden from Case Institute suggested that, well, why don't you determine it in the presence of all of the elements? So what we did is we set up a sample that contained all the elements in the periodic table, except, of course, things like the transuranium elements or gases or things of that nature. And this was undoubtedly the worst sample that anybody has ever tried to analyze. And we applied these methods to it, and they worked quite well, and that's what I called it, some rather unusual chemical analyses.
Yeah.
Well, we move on now. In your work, you published a number of papers and so on, and let's run through the list of those now, and you give us a brief description of some of the papers. Here I have, it'll take 2 sheets to put it on. Now these are just the papers that you published while you were with the AMP program, is that correct?
That's correct. Well, we've already touched on some of them, and as you can see, the analysis of beryllium oxide came out in a number of different parts. And this is the sort of thing I was mentioning before, that at this particular time we were working on beryllium oxide, and a number of these procedures I had used in the past for something else. Things that were not published was the application of these particular techniques to Bureau standard samples. And these methods were able to be applied to Bureau standard samples. Matter of fact, I analyzed all of the applicable samples, and almost without exception I was able to get the quote correct answer the first time I did it. Now, I don't know whether you realize it, but the establishment of the purity, not the purity, but the impurity content of a Bureau standard sample sometimes took several years. And these techniques were able to be applied immediately.
And many labs. They would have lots of labs, and I think the way, if I remember correctly, was that they would send out a sample to a number of labs, and they would take average all the lab results together, and that become the point of interest for the standardization.
I worked on some of those, and you're quite right. The big problem to set up one of these things is always to get a sample that's homogeneous, so that when you send it around to the various laboratories, the results that you get back are indicative of the method rather than the inhomogeneity of the material. It is quite a job to establish a standard, there's no doubt about that. And that's what I was really trying to do with these methods.
I see. Now, I know you and Jim McGree did a lot of work in the beginning. I believe Jim came up with the idea of the iron chrome aluminum alloy. Can you give us first being the tungsten rhenium alloy.
Yeah.
Can you give me a little history on that?
Well, at the beginning, which we should, it all started when Jim approached me. I think maybe it was early 1957 in the corridor outside of L8 or 6, and said he wanted to do some phase diagram research. And he was particularly interested in some high melting point materials. And as we continued this discussion, Jim made the observation of, well, we're going to have to do some thermal analysis work, but we don't have a thermocouple that'll reach these temperatures. And so he said, well, let's push the phase diagram research aside and start with a thermocouple.
Mm-hmm.
And he mentioned, let's take a look at refractory metals, and he particularly mentioned the element rhenium, which was a pretty much a novelty in the business in those days, and only recently discovered. So he set me about over the program to screen through high melting point materials in the refractory metals group and see if there were any good combinations for a high temperature usable thermocouple.
Mm-hmm.
And so we all started with that, and one of the things we had going for us immediately was the fact that in previous work the so-called gallium pool high temperature furnace had been constructed and was available so that we could reach at least the temperatures in the 4,000 degree range. So we started with available materials was another thing, and of course we had unalloyed molybdenum wire, and we were able to get some pure rhenium wire, and we started by calibrating this combination, and this also served to check out a calibrating system and to kind of shake down a furnace and the apparatus we needed to do the work. little later on, we got into looking at other refractory metals combinations, including tantalum and columbium and others, and we quickly came to the conclusion that our best avenue to follow was with the alloys of tungsten and rhenium. And that involved a second problem, and that was getting these alloys made into the form of wire, which we could use for the work. And we found a source for that would take the rhenium powder that was available and fabricate various percentages of tungsten rhenium. And as a result, we then were able to pursue these combinations and start doing some basic calibration work. And these charts we have here, these figures show some of the early work with pure tungsten versus pure rhenium, and then joining tungsten, for example, 20% rhenium with tungsten 3% rhenium and so forth. And later on we were able to get a tungsten 26% rhenium material. And as it turned out, in the end, why the best combination we came up with was a tungsten 26% rhenium on one leg and the tungsten 5% rhenium on the other. And we concentrated most of the work from then on that particular pair of wires. And these calibrations you see here go up now up to the 5,000 degree Fahrenheit range. So we were able to do this because we could convert that gallium pool furnace with tungsten heating element and eliminate the moly out of the system. And a lot of the initial work was concentrated on getting the furnace in the condition where we could reach these kind of temperatures.
Yeah. Now of course, you had to run the tables on there, and then you had to make up the chart,
Yeah.
the EMF chart.
Yes.
And how long did that take you to do that then, to get that in position where you knew that you could duplicate wire after wire and it would be at the same output?
Well, this work went on through the up through late 1959. We were pretty much in a position where we had a practical thermocouple that we could use, and we had not only a calibration curve, but we had calibration tables which could be used to make what we felt were pretty accurate measurements, determining the stability of these materials after continual heating and cooling, the effects on the EMF curve of this kind of usage. And we did prove that the combination, they were very stable through many hours of use. So we had what looked like a pretty practical thermocouple inside of a couple 2.5 years.
Now, after that, you finished that work and the end of the so-called AMP project. Has there been any further work done on this?
Well, as I indicated before when you asked me where I had gone from AMP, the AMP department, I went to Hoskins, who are a manufacturer, old-time manufacturer of specialty metal alloys, and have made quite a mark for themselves by producing highly reliable thermocouples such as chromalumel and other combinations that are usable up to the 2,000 degree Fahrenheit range. Mm-hmm. So Hoskins was a logical place to extend their expertise up the scale further in the temperature, and they were highly interested in the work we had done with the tungsten rhenium, and that's what my initial work was comprised of there, was to put this into a commercial product, and including the marketing aspects and whatever. And that took a couple years of work. And the important point I think here is that we did some cleaning up of the calibration figures in the tables, but basically the calibration is the same one that we developed early on.
There.
Yeah.
You mentioned that the Bureau of Standards is using that as a standard calibration this morning when we were talking. Now, Is that true? From the standpoint that they still, the calibrations that you guys worked out is essentially the same as it is now?
Well, after a number of years, and we were in contact constantly with the Bureau on these developments, the decision was made to accept this calibration as the standard for this particular thermocouple combination, and that's where it lies today. It is the original calibration has pretty much become the standard of the industry.
Okay, you mentioned the fact that Hoskins is making this now. Can you give me an idea of what the market might be and where it is?
Well, it has to be obviously a small market, but it's a very lucrative market in terms of profit. In my travels around, I've seen it in use all over Europe, certainly, and as well as the Far East. The Japanese are particularly interested in it and are one of the principal customers for Hoskins material. They are involved in a lot of high temperature research over there, as well as, for example, in the manufacture of artificial diamonds. And places like Kobe Steel and
they use the thermocouple then to measure the temperature in the diamond matrix, or what?
In autoclave, autoclaving part of that production system, yeah. So as well, the Chinese, strangely enough, are also manufacturing now this thermocouple combination in Beijing, and in fact, I haven't followed this lately, but I believe they are trying to market it through Canada. And,
well, that's the route, come through Canada.
Well, yeah, that's yeah. So at any rate, it's kind of a worldwide thing, and of course, in the early days, the Russians as well were doing a lot of work with this, and but they have never taken it into that I know of, into a commercial venture.
Well, that pretty well sums up the major part of the thermocouple.
What we thought we'd do today is look at some pictures we have in the shop showing some of the components, and John would comment upon them as we show the pictures. The first picture we have is
the graphite shop, showing the general area there. The lighting in that shop had to be explosive proof, and so did the motors on all the machines. And the vacuum system in there took care of the dust so that the workers would not have to breathe that. In general, that's about the extent of that. They made graphite dyes and components for the laboratories and manufacturing fuel.
Well, they also worked on other ceramics other than graphite, didn't they, John?
They did work on some, but not anything of the nature that would have been done in the special metals group.
Oh, okay.
All right.
Okay, here's a picture of the in the special metal shop.
Yes.
Right.
There's a young fellow there doing an operation in a dry box, and his name is Elmer Burns. And Elmer was in that shop for quite some time. The lower picture shows some of the filtering systems that were required to filter out all of the hazardous materials in the solutions that were used during the machining operations.
Okay. Here's a picture, John, that's interesting. I think it's the straddle grinder, isn't it?
Yes. Clay Brassfield referred to this operation, and I happen to have a picture of it which shows the straddle grinding of the beryllium oxide, the UO2 tubes in its early stages. and it was indexed by a small wheel at the top of that long slanted piece there to get the hex shapes. And the wheels were diamond coated and plated on the wheels, so they did a very precise job.
Okay. And here's one of the BEO reflector segments, I believe, from the...
Up the other way. That's it. Yeah, that's the heater 1 beryllium metal reflector that went inside the core and surrounded the active part of the core.
Okay, now the next one here is one that's dear to my heart. I was trying to get materials information on beryllium oxide, and I wanted to find out get a static modulus measurement on beryllium oxide. And I asked if you could grind a spring for me out of BEO. And I was surprised when it happened, and what a beautiful job they did. You can tell us how it was done.
Yeah, that was done with an ultrasonic, or what they call cavitation machine, and it was machined in its entirety by that method. It's one of the unique machines that we had the capability of using on this type of material.
The beryllium oxide is so, has such a high modulus and is so brittle, everybody was shocked when you take a BEO spring and spring the material like that.
It is really unique.
Here's some other components that you people made in the shops. You might want to comment on those a little, John.
Well, there's the metallic fuel element up in the upper area there, Bert, the circular parts. They were made and formed on equipment that was made in the general shops, dies and so forth. And then there's some ceramic parts of all types that were various generations of the development program, and a couple other items in there of interest.
A clad moderator.
Right, some moderator samples in there.
A sample, yeah.
Mm-hmm.
It's been evacuated and sealed, has it not?
Right, that was done, and the evacuation was done and welded in the electron beam welding machine. And pulled a vacuum.
And was this a fuel element sample?
Yeah, I think that is just
test?
a small fuel element cartridge type for test.
For testing.
This is machine shop.
This is, explain this one, John.
Now that's the general shop area where all the smaller machines were contained, and they did the general machining of most all materials except ceramics and the graphite. They made their dies and other components, as well as much tooling for the special metals, the special fuel element line. And in general, it covered quite a broad type of work in that area.
That was a big shop.
It was a big shop, yeah. That was only about half of the area.
Yeah. This looks like a tube sheet of some sort, John.
Contained in that general shop was a jig mill, which you see in the upper picture there, and that is machining a tube sheet. It's a very accurate machine, similar to a jig bore, only it's done horizontally. Mm-hmm. And that's a very tough material that is machining there. I think that had the is Inconel X with a high cobalt content. Made it very tough to machine. In the lower picture, we show a planer there, which gives you kind of an idea of different types of machines we had. It's small and compared to some, but a very versatile machine. Okay.
This looks like a EDM machine.
Yeah, you got that right. That's Bob Rau up there on the EDM machine in the upper picture. and that is electro-discharge machining. And out of the development of that type of work, they were able to do some pioneering work in the aircraft turbine business for them, and it's quite a unique piece of equipment. It erodes the material by spark discharge between generally a copper electrode and the workpiece. On the lower picture, we have a gun drilling machine, and we had a requirement for that for deep hole drilling, and it would do up to about 3/4 of an inch in diameter. We weren't making guns, though. Okay.
I've seen some of those EDM machines that could drill a hole so small you could hardly see it.
That's about right.
Okay, here's a picture of a surface grinder.
Yes, typical type of grinder that you might find in a real large shop, a big surface grinder. And that's just one of many. We had internal, external, and smaller surface grinders and honing machines. So we were well equipped for that type of work,
There's
too.
the honing machine down in the
Yeah.
bottom. Now here comes a big one.
This is a very unique machine. It's in a temperature-controlled room that is tightly controlled, I think about 2 to 3 degrees, maybe, I can't recall for sure. And it has optical measuring systems on it. And it's a Swiss-made jig bore. It's a very unique machine, and it's a very high precision. It has circular measuring systems within, trying to remember now, 2 seconds. And that is quite accurate, very unique. In the same room, go ahead, Bert. In that same temperature-controlled room, we have a smaller jig bore and a precision lathe to do very high-precision work that requires temperature control. And you see one of the workers there, I can recall his name, is Joe Finkbeiner.
Here?
Yeah, he's no, that's Dewey Stringer, I'm sorry.
That's Dewey Stringer, yeah.
And then Joe Finkbeiner's next, and then I don't know that third
This is Joe
gentleman.
Finkbeiner.
Right.
Yeah. I don't remember his name.
I don't recall him. We're getting old, Bert.
You know. Okay, here's another.
This was part of the solid moderator program. This shows one of the zirconium hydride tubes being machined, and the chips on that were very pyrophoric if they weren't controlled underwater, and generally you didn't see chips collect like this in any operation. They were kept collected and put underwater to make sure we didn't have fire. And at each machine we had buckets of graphite powder, because that's the only thing that would extinguish the flame if it got started. And that was done in the general shops, and we did tons and tons of that stuff.
Ever have any big fires?
Never had a fire.
Have some little flames?
No flames. Not that kind.
Now, here's a very young John Mundy. Maybe you can comment on that and some of the other people with us.
That was a bunch of eager beavers
Here's John.
that collared me to collect their suggestion awards. Starting on the right is Les Patton.
Okay.
And I don't know the next gentleman, or don't remember him. And that's Pete Hosky, and then Bill Bishop. And this guy's, he's not there.
Okay. What have we here, John?
We have a sheet metal shop. It's not a very good photo, but it's showing one of the big punch presses, and you see some of the busybodies there. They had various equipment in the sheet metal shop. They had ring forming equipment and cylindrical. Yes, okay. Let's see.
Oh, that's part of that, yeah.
You can see the cylinder rolling equipment.
ring
It's a
form.
center picture, a ring forming at the top, and they had various sizes in these types of machines. And on the bottom,
Turret punch?
yeah, that's one of the turret punches they
Yeah.
had, a Wiedemann turret punch.
This looks like a very complicated piece
Yeah.
of test equipment.
This is part of the CTF, or core test facility, insulation pads that went on the bottom plug, and they were instrumented. They had to be shaped and sectioned and fit properly, and we'll show you the picture of the part that they went on in a moment. That's showing the inside surface of those components, and they were fabricated in the sheet metal shop and instrumented in the instrument shop. And by the way, the guy that does the welding on the thermocouples, named Joe North, and he was about the only one that could do that consistently with a very good success rate.
Joe was a very talented welder.
Yeah, he had X-ray vision, I think, when he did those little needle point things on
He
with
did.
his weld torch.
He did. This is the assembly of that unit, isn't
yeah.
it?
He can point out there the segments showing those pads.
Those pads are down in here.
They're all over that section.
Yeah.
And up at the top, the dome piece.
This is the shield plug, right? At the
Right.
aft end of the...
Aft end of the reactor.
Okay.
Oh, the size of that? It was about, I think that was about 48 inches or more in diameter. I can't recall specifically that body there. And then the struts that are piped that extend out were for cooling and instrumentation exit
outs.
wires. Mhm.
Looks like some of the components that you made.
Yeah, these were some of the development components that were made, and some led on to actual products. And explosive forming.
Oh, the dies? Are these the dies?
These are the dies, the two upper pieces there that look like halves fit inside that ring. And then this other ring that you see there is fit down on the top. And the cylindrical piece there at the bottom was the starting form.
plug?
Starting form.
To be explosion formed, huh?
No, it was the starting cylinder that we started with. And all those parts had to be in and sealed with beeswax, and that area around the dies had to be evacuated. All the joints were sealed with beeswax. It had to be evacuated with a vacuum pump so that when the explosion took place, it did not compress air in those cavities where it was to form, or it would burn through. And that was one of the tricky parts of explosive forming.
What was the explosion device
The
used?
explosive was primacord, and we were limited to 100 grams in this operation.
Which way is this?
Yeah, this
way?
let's see, you got, no, turn it up the other way.
This way.
This way.
This way.
Yeah.
Okay.
Okay, this is the facility where we did the explosive forming. And you see a charge blowing water completely up in the sky there. And it was a tank that was two-walled with sand between the two walls and filled with water. And the die was always set on a pedestal down near the bottom of it. And the charge was placed in there with wires going out the control room, and they were set off at that point.
This
And
is
that's
the,
what you see.
the result, isn't it?
This is a result
Resultant piece of the explosion forming.
Yeah,
From this cylinder, right?
Right, one shot, getting those rings around there.
How precise could you make these things? Could you repeat?
Oh, the actual result was very close to what the die was, and the repeatability was very good.
Oh, good. What was this particular piece, do you remember?
I can't recall. They were looking at convoluted tubes for airflow into the reactor, and I think this was part of the development of that.
Okay.
This is part of the welding capability. You see welders at work on a large fabrication, which is the torus, and the upper part of the CTF facility. This is the large torus, and I think that was the exhaust part of it. And the diameter was in the neighborhood of, I'm guessing now, somewhere about 30 feet, or in that order. I can't recall exactly. The diameter of the whole donut shape.
This is on the high bay, wasn't it?
It's in the high bay on the iron construction floor there, where everything could be bolted down. And that floor was used quite extensively throughout the fabrication and erection of the parts that we made in Evendale.
Now they're TIG welding?
They are TIG welding, and by the way, all the welds had to be of X-ray quality. And that was pretty difficult in many cases. And these welders were all fairly versatile in that area.
There's their electron beam welding?
Yes, we have as I mentioned earlier, electron beam welding, which was done for, there was some very, very small stuff, and the canned stuff that I mentioned a while ago, where you had to evacuate the containment and then weld it so that there was a vacuum inside. And that was done in that EB welding machine.
You're telling me this is welding development? Or?
Yes, this is welding development. Jim Silfen is the operator there. Jim put together some equipment that we had bought and made an automatic TIG welder, which wasn't available on the market at the time. He took components from a couple of machines and a wire feeder and combined them to do automatic TIG welding on a very piece of critical material that we were working with at the time.
And back in the 50s, there were a lot of things that weren't available on the market that we had to
Much
come up with.
Much innovation took place in that shop that people never knew about because of its classification. And there were not answers on in the outside industry as a whole, because I was part of trying to find those answers. But they just were not available, and many times the people like grinding wheel manufacturers would say, you know more than we do. So we were out ahead of the game in many cases and didn't know it.
I think there was a lot of spin-off from those programs, John.
Okay. We had a clean room where all the components that had to be kept clean internally were assembled and welded in there. For instance, the core had to be taken into that room as components in sealed plastic and only opened up inside. The workers were required to wear nylon clothing and hats, gloves, and booties. And they had to change in a change room to get to go into that room.
Through an airlock?
Through an air chamber, yes. And we show Walter Golosky there in the top photo assembling the shield plug, which is upside down. And down in the lower photo, we see a welder welding up one of the shield cans that went on top of the reactor, the reactor, I'm sorry, and through the shield plug.
That was in the clean room. How big was
Right.
that clean room? That's a pretty big piece of
The
equipment.
clean room was probably a good 50 by 50. And it has a positive pressure, air pressure in there, so that outside dust did not come in.
This looks
Okay.
like part of a
That's the lower part of the cocoon, or CTF.
the
facility.
Containment vessel or?
Containment vessel is right. And showing the exhaust parts or tubes there. And that whole piece was manufactured in the shop with the exception of the dished head on the bottom of the dome.
Here.
That was purchased as from an outside bidder, vendor, probably Laddish, I don't recall. But it's 304 stainless steel, and the sheet metal shop fabricated those tubes, and the wells were done with TIG, and again, X-ray quality, and the wells were about, if I recall, 1.25 inches, or the wall is about 1.25 inches thick in that lower area there.
How big is, what's the diameter of that?
Diameter of that was in the neighborhood of, with the tube sticking out, probably 140 inches, something on that order.
Wow. That's about 12 feet, huh?
Yes.
Here's back in the high bay.
Right. This is another picture of one of the high bay machines, the vertical boring mill. And that happens to be the instrumentation ring that was part of the CTF, where all the instrumentation fed through little tubes in the ring. And that's on the 120-inch boring mill. And we had in the second high bay one boring mill that was 144 inches in diameter by 144 inches tall. So it was even bigger. We had 25-ton crane in this area and a 30-ton crane in the other area.
There weren't too many machines that big around, were there, John?
No, there weren't. No, that 144, it was a special order, I think. This is the shield plug in the high bay being worked on by two machines at one time, and it is not penetrating the inside of the shield plug, so therefore it can be out in an unclean area or a regular area. But you get two machines working on that thing at one time, which is pretty unique.
Yeah, that is. Well, here's the pizza oven.
Yeah, here's the biscuit oven. Bert calls it pizza. This oven was used, might mention how big it is. It's 12 foot high, 12 foot wide, and 20 feet long. And there's a car on rails that comes out. Its capability is about 2,100 degrees Fahrenheit. And during open house for families one year, we put on a demonstration out there with Big Fred Bentz baking biscuits in that furnace, and he had a table set up with jams and jellies and butter so that you could enjoy them. So that was quite unique.
Looks like a...
This is a core insert, solid moderator version of it, and it shows that the assembly in the high bay and the instrumentation that took place out there. You see the solid moderator at the bottom there.
Down here.
I think Otto Woike had
Down
something
here.
to do with this thing.
This is the instrumentation part above the moderator?
Right. And last but not least, we couldn't do without inspection. So we showed Mr. Hoxtel up there with his 30-inch comparator.
That's Lee, what? Lee Hoxtel.
Lee Hoxtel.
Yeah.
And he's still around. And then the lower picture shows the general area. And that was in a temperature-controlled room also. And he had all the necessary gauge blocks and that type of measuring instrument to support the work that we did in the shops.
John, here's a bunch of guys,
Oh my.
that some of whom I still remember,
you
and
could
some I
name 'em.
can't. But I'm sure.
Well, there's Jerry Moore in the center. I'm sure a lot of people remember him, the guy that, the older gentleman.
Jerry Moore.
And then
There's Buck Jordan.
Buck Jordan.
There's John Mundy.
Oh my.
John Tenenfeld,
Jake Keeney.
Keeney. I can't remember his name. Walt. Isn't that Walt?
I can't tell from here. Anyhow, hopefully some of them see their picture and
Joe.
remember it, yeah. Okay, this is first.
This is first.
Right.
Okay.
This is a picture of the shield plug and core as you come down in the transition area. There's a shield plug at the top, and then you have the transition area there.
Here.
Yeah, coming from there to there, and that's where the air entered in between those two. You see the control rods that, coming down through there, and then the active core, and it shows how the fuel elements would be loaded.
Would be loaded up from the bottom.
From the bottom, and that's in the high bay where it was assembled before shipment.
And then we
Turn
have
over.
picture on the back.
Yeah, on the back, if you can zero in on that, you can see the torus, the small torus, and the large torus, and the shield plug and reactor assembly in the background there, where they're assembling that at Idaho.
Oh, this is at Idaho? Or is
This is at
At
Idaho,
Idaho, okay.
right.
But all these components you made back here in Evendale and shipped
Right.
out.
Mm-hmm. Quite a task.
Well, John, I'll tell you, there was a lot of good machinists and manufacturing people in that organization that did a tremendous job. Good to have you here today,
Thank you.
and you'll be part of the bigger picture.
Hope.
Thanks a lot. John, let's put up on the screen the list of the employees in manufacturing shop.
Good
We'll
idea.
quickly run through them, and we'll just show them. Here's the manufacturing shop supervision. Here's you. Here's the employees of machine shop number 1.
This machine shop too.
Here's the employees of machine shop number 2. Here are the employees of machine shop number 3.
Okay.
Here's machine shop number 4. John, I know most of these people, but I can't put the faces with the names anymore.
No, neither can I any longer.
Here's machine shop number 5. And here's the sheet metal shop. John Carrier ran that, didn't he, John?
John Fleming, John Carrier, and Lauren Hudson. The difference between some of these numbers is that some are night shift and some are day shift.
Okay.
Like 1 and 2 are.
Oh, this is another shift on shop number 2.
That's correct.
Okay. Here's the well shop. This is shop number 2 again.
That's well,
Shop number 2 of the well shop.
Right. Second shift.
Second shift, okay. And finally, here's the special metals shop.
I might mention, Bert, that there were probably 3 or 4 other people in there, but I have no listing on them.
Okay, where's Elmer Burns? I didn't see Elmer's name in there.
Did we miss him?
He would have been in the.
Special metals.
Okay.
Yeah.
Quite a few people in that organization.
Right.
And they reported to
Gus Newsom.
Gus
for a long,
News.
yeah, at
and
one
Hita
point.
Luther Yost.
Right.
Well, thanks again, John.
You're quite welcome. Enjoyed it.
Really appreciated it. Thank you very much.
Thank you.
In the materials with the group at the A&P, we work with many toxic materials, and we also work with very hazard materials. Not only did we do it in the laboratories, but it was also carried out in the machine shops that were protected, and they operated under the conditions for hazard materials. We also had a hot shop, and that was also one of the problems we had of watching materials. Now, to keep everybody safe in the lab, in the neighborhood, we had a group called the Health Physics and what was the other name?
And Health Physics and Industrial Hygiene. Yeah.
Industrial Hygiene.
Right.
Heading up that, started in you joined the group in what year?
In 1952.
1952, and you worked there until you went to the A&P department, not the other department.
The Jet Engine Group.
To the Jet Engine Group. So when did you go there?
1979.
And who was speaking there is Ralph Hoffer, and we have Don Winkler over there. When did you join the group, Don?
I guess I joined about 61.
56.
Oh, 56.
56.
61 when the thing ended.
56.
Yeah, 56.
And then you worked there till how long?
30 years.
And you and Ralph worked together. Could you give me also some names of the other individuals that worked with you? Let's start this off.
I think as a group, we had at one time 36 people in our group. Gordon Boyle was a health physicist. Howard Perry was an industrial hygienist. Harry Coldy had charge of the laboratory operations and also community monitoring. We had a truck that we went out into the neighborhood and took air samples out in the neighborhood just to show negative data. Then there was Larry Brock, who had education and training. Pat Adams, who had the monitoring people in the laboratory. Ray Stewart, who had the safety group. And John Kale, who was one of our specialists in radiation protection, who worked for us. But let me correct you once, Earl. We didn't work with any radioactive material out in the machine shop. It was only material.
No, I know that.
Yeah. The radioactive material was always handled in the special metals shop, which was the L45 block and so on. And I might mention that when the Well, let me give you a little history about Building D. It was built in 1943, and it was the last building built in the Evendale complex. It was actually built as a aluminum foundry. And then in 1945, the day the war ended, everybody was laid off. All the equipment in the building were mothballed until 1951. And at that period is when the ANP contract was signed, and we took over the building. From 1951 to 52 and a half, the building was completely gutted. And as a result of that, the design was made. We knew we were going to be working with radioactive material, so a lot of effort and thought was put into how to design the building to safely handle radioactive material. Actually, the building was broken down into about 5 areas: the office area, the engineering areas, the laboratory area, and the shop area, a machine shop area. The laboratory area got the most effort put into the design, mainly because we knew what we were working with, we knew we were in an urban area, and we knew that if we had a serious accident, it would not only injure the people, our people working in the building, but would also get into the neighborhoods and maybe the jet engine plant and shut them down. So a lot of effort and design was put into the proper facilities to handle radioactive material. The lab was completely isolated in that it had its own air conditioning system, it had its own controlled exhaust system, which were all the exhausts going out were filtered through HEPA filters. HEPA stands for high efficiency particulate aerosol filter. And we also had a controlled liquid waste drain system that any water from the laboratory area went into holding tanks in the basement. And these tanks were never emptied until we took samples, analyzed it, and approved the disposal of that water. Any known contaminated water was put into 55-gallon drums, and these were shipped out for disposal. Same way with any known radioactive waste and so on. This was all handled special and shipped out and buried in approved burial sites. That pretty well covers...
Well, that's far more than I knew about that, Ralph. But I would like to ask you one question. What did you do with all those urine samples we used to give you?
We sent those to the laboratory to be analyzed. And I might say that all our air samples, all our urine samples, and I don't know of any overexposures to radiation. I don't know of anybody that suffered any radiation damage, but we did have a fairly tight program, and we've got a book of procedures that we followed. Donnie, have you got that book?
Yeah, I remember a lot of problems you used to give us on the things we wanted to do.
This is just our procedures on safe handling of radioactive material and the very toxic materials and so on. But we followed that to a T, and all the laboratory managers and so on cooperated in such a manner that we never had any problems along those lines.
Okay. Now, you want to pick up this information on the board here?
One of the key things that we had to do was educate the people who, not necessarily the engineers, because a lot of them had a technical background. They understood radioactivity. But we had a lot of clerical help, and we had a lot of lab technicians that didn't have the education and training to understand radiation. In our biggest job, we have two fellows in a group, and their assignment was education and training. You might turn that one around, and we'll talk about the biggest thing when you mention the word radiation is just it connotes a psychological fear, mainly because you can't see it, you can't smell it, you can't hear it, and you can't taste it. And as a result, the people who don't understand it, they're just very fearful of it. It's only when you explain all these the activity of how radioactivity works and so on, and the damage that it can do and how you protect yourself, is when they start feeling at ease to work with the material. Now, the other thing, the general public, they don't understand radioactivity either, and the mass media doesn't help the situation. For example, the 3 Mile Island incident. It was a serious reactor accident, but the mass media, they really blew that out of proportion, and they really scared everybody about radioactivity. And that fear is still existing today, 20 years afterward. People are just scared of reactors, and reactors can be handled very safely.
And we're going to have to use them one of these days.
That's right. Okay, then we also would talk about what radioactivity is, and you can flip that.
You want to move to another one?
Flip the back of that.
I'll flip the back now. All right.
What radioactivity is, and it's actually a process in which the certain nuclei undergo spontaneous disintegrations. Not all materials are radioactive. Just a very small percentage of materials are radioactive. There's very few natural occurring radioactivities. I think there's about 7 or 8 materials that are naturally occurring radioactive. In fact, we have a radioactive isotope in our body in potassium-40. Every time we eat a banana, or every time we take a potassium pill, or something like that, we actually are ingesting radioactivity. And the body contains a fairly large amount of potassium. A replacement for it's more important than sodium in the body, and you know doctors like to limit the amount of sodium for people who have high blood pressure and so on. But we get about 20 milliroentgens of exposure per year from the potassium-40 in our bodies. So we're also exposed to other natural activities, the cosmic rays that come from outer space. Nobody knows what causes them and so on, but we also get about 40 millirems per year of radiation from those. And then we have the natural occurring materials in the Earth, the uranium, trace amounts of uranium. You got, and as uranium decays, it has a very large progeny, or a lot of what we call daughter products. It actually decays down into radium, and one of the first item coming off of radium is radon, and you hear a lot about radon these days and so on. But this is natural occurring, you know. Every day when you go outside, you're breathing radon gas. And in a year's time, you would get an exposure about 30 millirems to the radon gas. Those are essentially the natural occurring isotopes of radioactivity. But then we're talking about material that we work with, and we mainly work with material called uranium-235, which is enriched uranium. It's one of the isotopes of natural occurring uranium. And one of the disintegrations coming off of uranium-235 is alpha radiation. I should say alpha-230. More comes off of uranium-234, but they can't separate them when they run them through the diffusion chambers to separate the various isotopes of uranium. But Don's got a demonstration for alpha radiation. An alpha particle is actually a helium atom. It has 2 protons and 2 neutrons in it. And since it has 2 protons, that's 2 positive charges, and it's looking to neutralize these 2 positive charges, and it will pick up electrons in the air. So an alpha particle.
Okay.
An alpha particle will only travel about 2 to 5 centimeters in the air. A piece of paper. We'll take a piece.
Put the paper in between there now.
Yeah, put a piece of paper. And a piece of paper will shield the alpha. So how does it shield it? Because it strips 2 electrons off of the paper. You can all the alpha you want on your skin and so on. No damage to the skin. It just picks up 2 electrons off of the skin, but there's no radiation damage whatsoever. The big problem with alpha radiation is if you get it internally. There's where it does 20 times more damage than beta or gamma radiation, and also X-rays, because of the ionization effect it does to large molecules. Let me give you an example of what it does to the human body. What radiation does to the human body when it causes ionization of the long molecules in the body. This was a piece of plexiglass, pure plexiglass, that we drilled a little hole in, and we had a 2 Curie cobalt source that we calibrated our radiation detection instruments with. And it would sit in our calibration well. We would raise the well to different levels. If we wanted something reading 100 millirem per hour, we would raise it to a certain level. If we wanted to read 10 R per hour, we'd raise it to a higher level and so on. So we calibrated our instruments in that manner. I just wanted to show you that what the radiation had done to that same piece of plexiglass. This was a very similar source boat, but had a years of exposure to the radiation. I don't know if you can get in very close and actually see that damage that's done. I might ask the question, did this become radioactive because it had a source in it and it's done out? And the answer to that is no. The only thing that can make material radioactive if you inject a neutron into the nucleus and you disturb the balance of that nucleus, then it becomes radioactive. But I can touch this, I can, it pulverized this material to a powder and so on. But it's not radioactive because it was strictly exposed to gamma radiation. And this is the same effect in the human body. Here is a source boat that was exposed for 2 years. And you can see the orange yellowish area in the center. And the damage done is a lot worse than the damage done to this one, to years exposure. But if you were exposed to the gamma radiation from to your body and so on, this is the same type of damage that takes place. It actually ionizes or breaks down that molecule to where it becomes a toxic material. A very small amount of exposure to radiation isn't going to make any difference because the little damage that would be done in a short period of time would be repaired by the body. The body's constantly repairing itself and so on.
So what you're saying is that don't worry too much about X-rays when you go to the doctor.
Because they're limited. If you could
right.
get a high exposure of X-rays, and it could do a lot of damage.
Yes.
And a lot of times in treating cancer, they'll treat it with high doses of X-rays and so on. They're actually killing the cancer tissues and so on.
Mm-hmm. But that's where they, they use a circular thing and
that's
pinpoint,
right.
But they don't damage the whole body, but they are damaging.
They try to shoot
right
it at different days. They shoot at different angles.
That's right. Yeah. Okay, what do you want to pick up next, Ralph?
Okay, so we talked a little about the alpha particle. Then
let's talk about the beta.
The beta particle. Both the alpha and the beta particle come from the nucleus of the atom. When a neutron splits, it gives off a proton and a beta particle. And the beta particle comes flying out with a lot of energy. There's usually gamma involved there. The gamma is the binding energy that held that nucleus together, so there's usually gamma energy coming off. The proton then stays in the atom, and it increases the atomic number of that atom by 1. So if you had hydrogen and you had an hydrogen atom that split, it would become helium and so on. And if you had uranium and you had a neutron split, it would become Neptunian, 1 higher in the atomic number.
All right, now we're going to back into another area. Well, we talked about that. Now let's talk about some of the areas that a lot of work was done, and you people played a very important part to be sure that no one received overexposure. By the way, while you're at this, you had film badges, did you not?
Right. Here's an example of a film badge. A film badge is only good for measuring beta and gamma radiation. And the reason for that is the alpha, a piece of paper would shield the alpha, so that photographic film that's in this film badge, if I can get it open here, the photographic film that's in this film badge is got a paper coating on it, so it certainly wouldn't pick up the alpha radiation. Here's a piece of the film that we pull out of the film badge.
Now,
let me explain a little more now.
Okay,
then,
fine. I was wanting you to do that.
I just wanted to show you the innards of this film badge. Actually, it has an open space. You can determine the energy of the radiation that the film badge is seeing because it has an open window. Can you see the open? Yeah, you can see the open window. And then it has a piece of plastic, the same plastic as the film badge. And then it has a piece of cadmium and a piece of indium foil. And they stop the radiation to a point, absorb the radiation to where you can determine what the energy level of the radiation is for beta and gamma radiation. Okay, I think that pretty well covers that.
That pretty well covers that, yes. Yeah, well, now we can move on into here, where you monitored this operation. And none of the work that we've done so far in these presentations, we have discussed the hot cells.
Right.
So,
well, let me talk a little before
talk about the hot cells.
Okay.
And so on.
Most of the work done in the laboratory was done with powdered uranium oxide metals and so on, uranium oxides. And after we made fuel elements and so on, we would send the fuel elements to Oak Ridge to irradiate them to see how they would withstand the neutron fluxes and the heat from a reactor. And then they would ship pieces back to the Evendale, and they would be put into the hot cell. This is the front end of the hot cell where everything's done remote. These are 3-foot thick, high-density concrete walls, and they have a view glass made out of leaded glass that's also 3 foot thick. So everything is done by 2 remote handlers using just these 2 fingers. So anything that you can do with 2 fingers, you could do in a hot cell. Here is the back end of the hot cell.
Let me show you the back end.
Again, it has 3 doors on it. There's 1, 2, and 3. 1 was the area, cell 1 was the area where we loaded up our hot cell material. The other 2 cells, we prepared metallography samples, and then we polished them in there. Here is another picture of the back end of the hot cell where a cask coming up from Oak Ridge is loaded. And
back end of the door.
That's the back of the door, and it gets rolled into the hot cell. That's Stu Layton that's unloading that. And here's another picture of Stu, and we're sort of dedicating this to Stu because Stu had died of a heart attack about 4 or 5 years ago, and he did all the work back in the hot cells, the main work in the hot cells. A very creative individual.
Yeah, he did design a lot of the equipment, I know. It was used to help out because it was hard to handle a lot of the things.
Right. You couldn't handle the activity in this material. Within maybe 10 minutes, you'd be dead from radioactivity. That's how hot some of this material was. And that's why you had to use the hot cells to handle the material.
And now we're going to show you the best dressed man in the AMP program.
That was in my younger days. But apparently there, what I'm monitoring is the cell before they put something in, make sure that it's clear. We always check them out before and after, just to make it safe for people to be able to work in there and load them up. There's always a lot of monitoring to do. On the other side of the operating side, even we took air samples just to make sure there was nothing that could come into there. And of course, we took them on the hot side too.
But also for surface contamination, you know, this radioactivity, if it's a powder or dust and so on, if it gets on the floor, you can track it around. And as a control that we didn't expose anybody unnecessarily, we were constantly taking smears on the floor to determine if any material was being tracked out. We also did this in the labs with the powdered materials also. Did I mention before that the labs were specially designed that they were under negative differential pressure with the rest of the building? That meant all the air from the rest of the building was being sucked towards the lab. So if we did have an accident to occur, that it wouldn't get away into the rest of the building. The individual labs themselves were under negative differential pressure with respect to the hallways that they were in. So all the air was flowing from the rest of the building to the hallways to the individual labs. Then inside the labs, we would have hoods and dry boxes. They were under negative differential pressure to protect the labs themselves. Mm-hmm. So, and we had a very elaborate air conditioning control system that if anyone left the door open for more than 20 seconds, it would measure the differential pressure in the room and automatically shut down the air supply to maintain a differential pressure, a negative differential pressure. So these facilities were well thought out, and as I say, I don't know of anybody that got an overexposure to radioactive material.
I admit, I never heard of anyone being sick on that. Not only did you have to take care of us from the radioactivity, you also took care of us in case we had a fire, right?
Yeah, we had a volunteer fire department. It was headed up by Ray Stewart. And there's a picture of our volunteer firemen. Twice a year we would have exercises, and we would plan on different accidents happening and so on.
Okay, now we'll move on. I think that we could end it up by Don and you demonstrating the use of Geiger counters and other body counters that you may have here. So,
this is about the most sensitive instrument that we have. This also has a speaker on it that you can hear every burp. So as you move a source close to it, so that was one of the methods of protection, of human body protection from radiation, is distance. If the radiation falls off inversely as the square of the distance. So the farther you get away from the source, the less radiation you would receive. Other protective methods were time. If you had a job to do that's fairly high radioactivity, you would try to do it in a hurry. Or first of all, you would practice so you wouldn't make any mistakes of dropping material or spilling material and so on, if it were very hot. Then you would practice ahead of time that you could get the work done properly and so on. And then you get in there and do it with a minimum of time so you kept your radiation levels down. The other method was shielding. We have a piece of lead. We'll turn yours on. Yeah. This will create like a static, but watch when I shield it. Well, that's a.
Here. You sure that's lead, Ralph?
Yeah, that's lead, but that's an awful thin piece of lead. We didn't practice.
It's also a fat detector.
We should have that lead brick here.
Get the other one.
I also brought along some uranium ores. Here's one that's fairly hot.
This one.
You want to use this?
Get the other one now. No, the other one now.
Yeah.
Oh, okay. Let me just show you. This probably has enough uranium in that it would be cost effective to refine the uranium. Also got some very low level amounts. So it wouldn't be very cost effective to mine this grade and to recover it, but this is a fairly high level one. Also a third one that we have. It's a little higher than this one though. So those are different grades of radioactivity. Also,
I think that's interesting. That dish there represents the technology that we had, but a lot of times they're using Fritz before the 1940s. Is that true there?
Yeah, that's right.
And a lot of people had those in their house and didn't realize, they thought it was pretty, but they did not realize the problem that might have with it.
Very, very beautiful colors. It's called Fiesta ware. And if you had a serving of 12 and had these all stacked up with the saucers and the bread plates and the dinner plates and so on, you could actually get about 150 milliroentgen per hour off of these. So they've since been banned by the Public Health Service. About 1950, they banned these materials.
They're still around.
They are still around, but people don't realize the hazard associated with them.
But that's only in the red and sort of light yellow colors.
There's a yellow. This is an orange. Yeah, this is uranium salt, and the yellow is a different uranium salt. In fact, most yellow brick and homes contain a low-level amount of uranium. It's a uranium salt. Okay, Earl, that's all.
Well, we've learned an awful lot about what you did down there. I often wondered what was going on. And I thank both you and Don for coming in today and adding this portion of your presentation to our general presentation we'll have.
Okay, very good.
Thanks a lot.
Thank you. Okay.
Hi, my name is Bob Evans, and I'm here with Jack Simpson today to review, continue to review some of the activity that went on in the ANP program, Aircraft Nuclear Propulsion, between the years of 1951 and 1961, when General Electric was in control of the program. Our specific objective today is to review a little bit about reactor physics and what it means in terms of the ANP program, and also to review what went on at Evendale in terms of critical experiments. And Jack will explain what critical experiments are a little later on. As far as when we talk about a reactor, a nuclear reactor, as concerned with aircraft nuclear propulsion, we're talking about a reactor core that's primarily composed of uranium-235, highly enriched. And highly enriched is, in our case, is about 93.4% U-235, with probably the rest in U-238. We're talking about a reactor that's made up of this fuel, and we're talking about a reactor that's made up of a moderator being necessary to slow down the fast neutrons that are born at fission in order that they may be absorbed by the U-235. We're talking about a reactor that contains a reflector being necessary to reflect those little neutrons that are trying to escape the core back into the core. We're talking about a reactor that has a control system, a system that allows us to control the level of power in the reactor by controlling the neutron flux, and also to provide a means of shutting down the reactor should the reactor become uncontrollable or for some other reason, by way of using safety rods. These rods, in our case, and most of ANP cases, were boron, and boron, of course, is a high absorber of neutrons, especially thermal neutrons. We're talking about a reactor that has to have its fuel elements cooled. When the reactor is fissioning at high rates, it's producing a lot of heat. This heat has to be removed or the reactor will melt down. In the case of ANP reactors, we're talking about air cooling. And this air cooling is provided by a jet engine. And of course, we're talking about sensors that we use to monitor the level of neutron flux and also to tell us what the period of the reactor is and other things concerning temperature, et cetera. What does a reactor do? Okay, that's relatively easy to explain. U-235 fissions, and it fissions by capturing a thermal neutron. Thermal neutron, in the process of this capture, splits the nucleus of U-235 into two parts. These parts have relatively high kinetic energy. This energy is absorbed in the fuel element proper and is translated into heat. The moderator is essential in order to slow the neutron down. And of course, the reflector is trying to keep the neutrons from escaping, and the airflow cools the reactor fuel elements. Critical experiment is an experiment that's set up to try to simulate an actual reactor design with similar materials and similar or exactly the same fuel. And the idea here is to try to produce the power distribution and the flux levels that you'd expect in a full-size reactor, but at a much lower power. We're talking of powers levels of 1 to 10 watts, whereas our full-size nuclear reactors are probably going to run at anywhere from 20 megawatts up to 100 megawatts, depending on the design. In a critical experiment, we want to provide means of changing these configurations. If the reactor designer hasn't designed things exactly correctly, we want to be able to manipulate those configurations in terms of fuel and moderator and structural materials in order to see what the effect on the power distribution and power generation is. Of course, we want to control the power level with our control rods, neutron flux being a significant factor. We want to measure the neutron flux in the reactor in order to determine exactly what the power level is. Of course, we want to measure the flux distribution to find out where the power is being generated. The purpose of all this, of course, is to verify design calculations to make sure that when we go and actually build a reactor and put all the time and effort and money into doing this, that it's going to behave the way we expect it to behave. And also, when we operate our full-size reactor, we were going to have to know what the how effective the control rods will be, and the critical experiment will allow us to do that. And then, of course, it'll allow us to measure how effective the reactor is in terms of maintaining its capability of maintaining its power level over a period of time. And this is determined by measuring the reactivity of the system. And the so-called parameter, which is called K effective reactivity, if that's equal to 1, the reactor is just critical, and any values greater than 1 means that the reactor has the capability of being put on a positive period and have its power level increased. We talked about reflectors. What does a reflector really do? This chart gives you an idea of what's going on. If we have a core that's bare here without any reflector, these are reflector sections here, usually beryllium, or certainly beryllium in all our cases, but they possibly could be other things. A and P only use beryllium. If you don't have this reflector, you can see what the flux distribution looks like. And you can imagine that if you had a fuel element in the center of the core, you're going to get a very high power generation. If you had a fuel element out here, you get a low power generation, and that's not too good for trying to get a uniform air temperature out of the rear of the reactor. By putting a reflector in, you allow the neutrons that are trying to get out are reflected back. This skews up the outer part of the flux curve, and of course gives you a much better distribution of flux across the reactor and a much flatter power distribution. We can then further compensate for the fact this is still skewed by adding, say, more fuel out in this region of the reactor to get the power level up. We talk about reactivity in terms of what it does to the system and what it is in relation to addition of uranium-235. In general, if you compare a reactor to a reactor with U-235 in it to a reactor that's made up essentially of U-238, which of course some of the big early piles were out at Hanford used to produce plutonium. The Hanford piles were gigantic because they required the use of 238, which has almost no cross-section for fission. But the residual U-235 that's natural in U-238 did most of the fissioning. So, since there's so little of it, it required a great big reactor to get it to fission. In terms of the effective multiplication, the capability of the reactor to generate more neutrons than it absorbs, we look at a curve like this, which was actually a curve for the Heater 3 reactor. We're talking about plotting pounds of uranium installed versus the effective reactivity. And the point being here, we're shooting for a design characteristic. Of course, we want it to be greater than 1 because we want the reactor to be critical and be able to generate, and we want it to be greater than 1 to be able to generate a positive period. The design characteristic of the Heater 3 was a multiplication factor of 0.03. This is a lot of multiplication. The desire here is to be able to override things like xenon and have the capability of operating the reactor for long periods of time. Xenon, of course, is a poison that builds up after the reactor is shut down. Jack will probably talk a little bit about this later when we talk about reactivity periods in relation to effective multiplication. If we're just at or near an effective multiplication of 1, the reactor period, though it's possible to get a reactor period, is going to be very, very slow. And of course, as the reactor, as the effective multiplication is increased, we can get a much higher period. It's important to control that period so that the reactor does not go critical at a faster rate than we want it to. We talked about cross-sections a few minutes ago. Give you an idea of what a cross-section means in relation to from one material to the next. We talk uranium. These are all of the odd materials are fissionable materials. The even one, of course, U-238 is relatively non-fissionable, and you can see why. The fissionable materials have cross-sections of over 500 barns, particularly plutonium, whereas the uranium has a cross-section of very low, down around 10 barns. You can't imagine you're going to fission uranium with fast or thermal neutrons. Poisons, the idea being to absorb as we mentioned, the neutrons that we want to control. There are three very prominent materials that are available to use as poisons: boron, cadmium, and europium. Some of these are very rare. Most of the work we did was with boron, which has a cross-section for absorption of 700. But you can see that europium would be a lot better, up around 4,000. Up to this point, we've talked a little bit about reactor physics. We're now at the point where the AMP program has been brought to Evendale, and we're contemplating doing critical experiments in Evendale facilities. And Jack, I know you were involved in this program practically from the start.
Right. When we started in 1952, basically trying to create a reactor design, you've got to remember that in those days, computational power as we know it today just did not exist. Today we use neutron calculations, multi-hundreds of groups. In those days, a big deal was a two energy groups of neutrons, calculations solved by banks of people standing around pushing or sitting around pushing mechanical calculators. That meant that the entire theoretical basis for reactor design was pretty shaky. So as a consequence, much of the design had to be done empirically or experimentally, which is where the critical experiment function came in. The recognition was made that we would have, when we moved to Evendale, Ohio, we would have to have that facility, and correspondingly the back end of Building D, which Bob is pointing out there, which consisted of a bunch of sand bins for a foundry which had been in place during World War II, was converted. Part of the conversion area involved making or creating two cells in which we would install critical experiment rigs. Critical experiment rig is a device that we're going to show a few pictures of in a little while that actually contains the uranium fuel that Bob's been talking about and all the other goodies. Here's a layout of the facility in Building D. There was two cells in it, the cell 1 and that cell room 7. I don't know if you can read the lettering, but it's not important. It's basically the cell which is colored in the lower view. And immediately adjacent to the cells were the places where the fuel elements were put together. Now, and also immediately below there, when we put it on area 6, that was a control room from which the reactor function was controlled. In the case of water tanks, we would control the pumps and rods from there. In case of moving tables, we control the table, all and viewing the process for the most part with a closed circuit TV. Remember, this was in the middle 50s. So, and all the rest of the facility you see there in the chart was basically supported, provided to support the activities, trying to measure the power distribution within the reactor. Again, computational facilities in those days were extremely limited. Only during the last 2 years of the ANP program did we have a computer that anywhere close to what we now today recognize as a big-time computer. And so we had this facility where we constructed the reactors, exposed the fuel to the measuring devices in order to determine the power distribution. In 1953, as I mentioned, the program the entire A&P program was redirected, and one of the first things we needed to do was to embark on a proof of principle set of experiments, so-called heat transfer reactor experiments, which Bob has beside him there showing the concept. It basically consisted of a large tank of water perforated by 37 tubes through which air would flow. In each of these tubes, a fuel element would be located, and control rods would then be inserted in the interstices between the air coolant tubes. These control rods, as Bob mentioned, consisted of boron carbide, boron oxide, used to adjust the multiplication of the reactor, or the K. So we had to, next step was to come up with the concept of what an experimental fuel element would look like, which is shown here. It's a multi-stage one. This isn't actually the first one, but it's the second one. And it consists of a series of 10, I believe it's 10, maybe it's more, maybe it's 15 on the heater, 18 on the heater 3.
Yeah.
Horizontal stages in the horizontal or flow through a direction. Air went from left to right in this model, and each of those segments consisted of a series of concentric rings. These rings were fabricated out of material which we talked about a few minutes ago, which was the nichrome-clad, uranium oxide meat. Now, the design of the reactor was such that we could be represented, the geometry could be represented very simply in a tank of water. It so happens that at Oak Ridge there was a facility created during the early NEPA days which had a water tank in one of the cells. Arrangements were made to borrow the tank for a couple of months, and a mock-up of the reactor was constructed and installed in that tank. You see here on the chart that picture of that mock-up, the 37 tubes simulated there, and around it is the tank in which the water would be placed. In August, latter part of August 1954, the same facility was recreated in Cincinnati with different kinds of fuel elements, representations, beryllium reflector from the very beginning, which, can you point it out here, Bob? Yeah. And the rods you see sticking down in the interstices there are the control rods, which are moved up and down by either motor driven assemblies or by spring force in the case of a rapid shutdown mechanism, otherwise called scramming. At the bottom of the tank was a 12-inch valve. You can't, it's hidden there, but when the scram function was performed, that dump valve opened and all the water ran out of the tank into the basement corridor immediately below the cell. Well, this water was took a long time to prepare because of the purity required. So we basically would shut the reactor down by just scramming the rods and not dumping the water. So a lot of experiments were performed. That facility operated for about about a year and a half.
You remember
Sure.
that little flapper valve device we had there? There's a big story associated with that.
Oh, Lordy, yeah. One of the things we needed to do in order to get permission to operate a reactor in Cincinnati was to analyze all possible accidents that could befall us in operating this thing. This is so-called safety report or hazard report, whoever, you're a half-full guy or a half-empty guy. And one of the things we had to evaluate was what would happen if the pump proceeded to pump the water too fast into the tank and it overflowed into the top of the tubes and got into the inside of the tube. So if you see if that water got too high, went up over the top here, and got down inside the tube, what would happen? Well, what would happen was not nice. So we had to provide a way of obviating that. The way was determined, okay, let's put a standpipe outside the tank and let the standpipe be the safety valve. Well, we did, and we then failed the various water pump rate protection devices to see where the water would stop. Well, it didn't stop soon enough with the initial height on that standpipe, so we cut off 1 inch. Now, this was a 12-inch stainless steel tube, 1 inch thick, and we cut it off 1 inch at a time. I was sitting in the cell with an Air Force guy, and we'd say, okay, we'll cut to here, and somebody would come in and cut it. We'd try it again, still wasn't right. So
this was done with a standard hacksaw, too, if I remember correctly.
You got it. I wasn't running the hacksaw, but it was cut with a hacksaw. So finally, after a few days, we finally got it down to the level that was considered acceptable, and under these simulated accident conditions where the low pump kicker in failed, and we kept going with the high rate pump. So we got rid of that, and then we proceeded to load the reactor incrementally, and this is you're seeing here a cross section of the first reactor, the heater 1. 37 tubes arranged in the pattern that's quite apparent here. The interstitial regions, some of them had absorber rods of boron, and one of the places there, right there, was a tube which allowed us to start the chain reaction by inserting a source. In our case, we were using a source made of polonium beryllium. Polonium is an alpha emitter. Striking beryllium creates neutrons. The neutrons were then used to initiate the chain reaction and provide a minimum level for our instruments, because we needed to know exactly what the neutron level was. So as we added fuel, uranium around there, that apparent level of neutrons kept increasing and increasing, or multiplying, surprisingly enough. And that multiplication factor we referred to earlier, which was so abysmally low in the initial Oak Ridge experiment, basically tracked much better. And we achieved criticality with roughly 33 tubes loaded with fuel. Bob has got to here now a representation.
Let's put that chart up. It's gotten out of.
Okay.
That's the chart you were talking about, I think.
Right. So, yeah, this as we loaded fuel in the fuel elements, I should say, the inverse of the multiplication, which is handier to plot than the actual multiplication itself, since that gave us a scale of 1 to 0 instead of 0 to infinity, is shown here. After loading the initial 7 tubes, the center tube and the 6 surrounding it, we had a multiplication of about, let's see, 8.85 was about 1.2. And we used that as a basis, then we continued on, then we actually got a multiplication of about 3, and so forth down the line. Each time you measure how many neutrons am I measuring at a given detector, or what's the neutron flux, compared to what it was without any fuel. That what it was now with what it was with just the source is called a multiplication. Plotting it, the reciprocal of that multiplication gives us this curve, since we know that when the reactor will be self-sustaining when the neutron flux is there and the source, the artificial external source, has been removed, which is represented by this condition here. So we march down the curve looking like that, adding each of those large black dots represents a fuel loading increment.
And our desire is to somewhere get down here and then be able to extrapolate to the point where we think it's going to go critical.
Right. Now, the chart has been simplified somewhat because there are actually 2 multiplication curves generated as we go along. One with the control rods totally withdrawn, and one with the control rods totally inserted. So that as we go down, we will make sure that when we get to the point where we're critical with the rods out, we are definitely subcritical with the rods in. It's a most desirable condition.
You might add that a lot of this procedure was developed by Enrico Fermi during the first critical experiment, which was conducted at Chicago.
On my birthday.
On your birthday. Which was
Seriously.
Was it?
Yeah, absolutely.
Were you there?
No.
was a big stack of graphite and uranium metal with the control rods in. The stack was about 25 feet in diameter and about 20 feet high. But it was natural uranium, and it just took a lot of uranium to get it to go critical. But they followed basically the same procedure, and those procedures essentially went down through time to the point where we did almost the same thing.
Mm-hmm. Yeah, there's, without getting into all the esoterics thing, it's a factor of you don't want to double more than double a multiplication on any successive step. All right.
It's also a factor that it's going to tell you pretty fast if you're not doing things right, because if that curve starts diving in someplace, you know, with only a few tubes in the reactor, you know you probably haven't gotten the loading right somewhere along the road.
Or you've got some bad instruments.
Right.
Yeah. Okay, here we see the representation that was used in the critical experiment facility for the fuel element loading and for the purpose of power measurement, uranium fission power measurement. Now, I've got it over here. You got it? There's one more. Yeah. Now, you're looking at an assembly of 6 concentric tubes. These tubes are made out of 10 mil thick nichrome, 10 stages long or high, which corresponded, in our case, its reactor was on its nose, to the airflow direction, although no airflow was obviously used at these low power levels. Around each of these cylinders, we would wrap additional nichrome, thin sheets, 1 to 10 mils in thickness, and uranium, and fasten the uranium and metal on there with standard straps used to strap insulation on pipes. Turned out to be a very economical way of doing it. And after each cylinder was loaded with its assembly of uranium foil or fuel elements and nichrome, the 6 were assembled on a supporting cross member down there, and then the entire assembly was inserted into one of the 37 tubes we referred to earlier. Now, in order to measure as we talked before, one of the things we needed to know is how does the fission rate distribution vary as you move through the reactor. From a thermal design viewpoint, you want that fission rate distribution to be as uniform as possible, since that would represent that gets you closer to the ideal thermal efficiency of your heat generating machine. So that became our paramount measurement need. Now, the way we would do it is you put uranium, bare metallic uranium in place on these fuel elements here, and then we would place half-inch squares of aluminum, something like this. Okay, put that in front. Yeah, put that in front of them. Okay, in intimate contact with the bare uranium metal. Literally, it looked just like that, half-inch squares on tape and wrapped around the fuel element. Okay, then the reactor, that foil was a foil-impregnated fuel element was loaded in the reactor. The reactor was run for approximately 20 minutes. It was very precise timing needed. And the reactor shut down, the fuel element quickly removed from the reactor. These foils stripped off and placed in a counter. Now, what had happened while they were in there, these half-inch square foils had captured fission fragments due to being the intimate contact between these aluminum foils and uranium foil. These fission fragments were then decaying. Now, so remarkably enough, we call them catcher foils. They caught the fission products, fission fragments resulting from the fission. The radioactivity measured in those foils was then a direct measure of the fission rate activity occurring in that spot immediately below the foils. Therefore, by measuring these foils throughout the reactor, all other conditions being equal, power level, time, and so forth, the relative radioactivity of each foil would then be a measure of the uranium power distribution generated throughout the reactor. with that, our thermodynamics folks and our metallurgists could then determine, okay, in this part of the reactor, we need to have so much uranium in this particular fuel element at this particular location. These specifications were then given to the manufacturing folks, and they would proceed to fabricate the high temperature materials using the specifications which we had developed this way. And again, I want to reemphasize that we were limited in the calculational capabilities. That's why it requires such extreme measures to get good power distribution measurements in the reactor. We then embarked, since this became quite a problem in terms of controlling human exposure to the radiation. You couldn't help it. Later on, we developed techniques to load perhaps 400 to 500 foils in a reactor for a given run, and mechanized counting techniques connected the counters to the beginning computers or the initial computers we had there. And that was done in order to reduce the human radiation exposure associated with the folks doing the experiments and removing these foils from these, because they were radioactive after removal from the reactor.
Not only that, Jack, we constantly use the same fuel from one experiment to the other, and there's bound to be some residual activity.
Right. There were times when we would just plain stop operating for a while, for 2 or 3 days, and let everything cool down, so that when we next started to load some catcher foils on the fuel elements, the exposure would be reduced.
I remember we really had to take a lot of pains, and we'd bring it up on a period, and we had to turn the corner very precisely so that we didn't overshoot and had a nice flat profile.
Right. The idea was, we had to reproduce conditions. The total exposure, the total number of watt seconds, had to be maintained or known from one exposure, one run to another, because we wanted all these measurements to be normalized in order to provide this precise power distribution measurement needed for the fuel element loading determination. Okay. Now, one of the other unknowns at the time, it turned out to be really unknown, was what effect the temperature of the moderator water would have on the reactivity, or the K of the reactor. Initially, it was thought, as the water gets hotter, the density is going to go down, therefore the reactivity will go down. Well, it didn't quite work out that way. So we had some heaters installed in our tank there, and steam heaters with electrical support. And we started to heat the water up in an experiment one day, and after doing a lot of preliminary work, and lo and behold, we had to keep running the control rods in, which meant the reactivity kept rising. We kept going it in, running it in, running it in, and after a short period of time, we said, wait a minute, we have to stop here. We had the rods too far in. So we shut down, and we just changed the initial conditions. We added some control rods in that were static and just
the manual type.
Manual type. They just went in and stayed there. They didn't get moved, because at no time could we ever get into a condition where our control rods could not shut down the reactor. So this gives you a picture of the change in reactivity as a function of the water temperature in the reactor tank, and it's going from southwest to northeast indicates that reactivity is increasing as water temperature goes up. You can't read the numbers on the grid, but that's what it's saying.
I think we went up to about 150 degrees.
Yeah.
Eventually.
Right. In several steps.
Right.
Because of the, you can't tell it by looking at the side there, but that's a non-trivial change as a result of the water temperature.
In fact, this can be a positive thing also. As time went on, we found that we were getting so much xenon buildup that one of the only ways to get the reactor started was to heat the water up.
So much for that water facility, we kept it for a while, and all the experiments were needed were performed. The power reactor was designed, built, and started to operate in Idaho at our test facility out there. So it became quite apparent that, okay, the heat transfer reactor experiment #1, which is what we're doing, was a success. The fuel element we were able to design fuel elements. We could run it at temperatures appropriate to the needs of the program at that time.
Do you remember how many hours we put on that critical experiment? It was a lot.
Oh, the critical experiment? Yeah. Oh, hundreds.
Hundreds.
Yeah. Hundreds of hours.
And normally they would run about 20 minutes, I think, per pop, right?
Our exposure for our foil exposure
yeah.
was a 20-minute run, right? And we get maybe 3 of those a day.
Yep.
And so there were a lot of them made, and but we'd served our purpose. The reactor was designed, was operating. There was no more real need for the critical experiment in Evendale. But at that time, the design requirements of the program had moved on. That water was nice to prove a principle, but it was not realistic to think about that for an aircraft propulsion device. So the next consideration was, well, okay, how else can we get a hydrogen in around the uranium? Now, the moderating function that water provides is due to the interaction of the high energy neutrons, and Bob talked about earlier, interacting with the hydrogen present in the water.
Just like billiard balls, right?
Exactly. One of the things was considered was, well, maybe we can hydride metals. So the idea was, well, we can hydride zirconium. Zirconium is a very good hydrogen absorber. And actually, you can get as much hydrogen per cubic centimeter in zirconium as you can in water. Some of the other metals, you can actually get considerably more. And what you're seeing here is a representation of the reactor with hexagonal cells of zirconium hydride with roughly a 4-inch or 3.5-inch diameter hole through them. Into these holes were then placed the fuel elements that we just finished talking about, and that zirconium hydride hexagonal cell then took the place of the water. Otherwise, everything else was the same. Surrounding this structure was a beryllium reflector. Okay, the mock-up that we did for that reactor was constructed in the other cell from which we did the water tank. In this one, we divided the reactor with a line passing right down the center line of the reactor such that the upper half of the cylinder was restrained on the second floor of the cell. The lower half was mounted on a hydraulic piston, similar to that which is used in garage lifts and so forth. And the reactor would be brought together remotely from the test cell or from the control room at the top of the steps there. And actually then the hydraulic lift would lift the upper half off of its support pads by about 3/8 of an inch. And the reactor, all further activities on the reactor were then conducted from the control room, as I mentioned up there.
Did we have the big concrete doors in this facility?
Yeah. Okay. Yeah. Good point, Bob. The other cell which we started had the equivalent of 5 feet of concrete mounted on hinged like a big bank vault door in the test cell, and that was manually operated. Well, Bob and a few other guys and myself got pretty tired of pulling that door open and closed all the time. So it got a motor put on it. But we had something to say about the construction of this cell. So we had a door mounted or created on the one wall of the cell. It was roughly 100 tons of concrete, and was moved back and forth in which to load things into the load structures into the cell. And then we had a very small personnel door up there at the top of the steps from which our people went in and out. Okay, here's a picture of a table facility which was basically our next experiment. It's not the exact facility, but it's close enough. It consists of a series of, a whole stack, I should say, of hexagonal aluminum tubes into which we would stick uranium, stick is a very gross word, place.
Insert.
Insert, good word. Uranium, zirconium hydride, beryllium, beryllium oxide, or whatever. Each segment of this thing would have half the reactor on it, and one half would be fixed, the other half would be remotely closed with the other half, and we would then have a close to a critical assembly. And then the control rods, which are mounted out here, would then be removed or inserted depending on whether we're having fuel or absorber to bring the reactor critical. That facility, which is sort of like this one here, is one which we used for the A&P program, initially for the zirconium hydride program, then for the fast reactor, then for the beryllium oxide reactor program. And later on, after A&P was canceled as a side issue, that facility was then moved to Idaho, where we did fast reactor experiments under the NMPO, or follow-on to A&P. And when the NMPO program was terminated, that facility was turned over to another contractor. I don't know who it was. And they continued to use it for another 15 years. And before it was dismantled in the middle 80s, it was the longest running experimental facility in the United States.
Just another example of GE quality.
Absolutely. It was a real top-of-the-line design, including the hydraulics, Bob, which you did.
Right.
Okay, here you see a picture of the beryllium oxide fuel elements, which were later used for the latter part of the program. Was decided that metallic clad fuel elements were just not going to cut it in terms of turbine inlet temperature for the various mission profiles which we were trying to achieve. And the only way we could get it is going to a higher temperature material, namely a ceramic, which in our case turned out to be beryllium oxide. And we had to start doing critical experiments on beryllium oxide reactors. We would have pure beryllium oxide, and we would cut up our thin uranium metal foil, stick it inside the tube, and that formed our fuel element simulation.
The actual tubes, the beryllium oxide tubes, this happened to be fuel tubes, and their appearance is dark,
right,
blackish compared to a white.
Beryllium oxide is white, yeah. Right. Okay, yeah. Okay, now here's a picture of the ceramic reactor mock-up. Here's the hexagonal tube structure I alluded to earlier. Surrounding it are 5/6 of the reactors consists of beryllium oxide tubes with uranium metal inserted inside the tubes. The upper sector there, roughly 1/6 of the reactor, was actually beryllium oxide, uranium oxide fuel elements. And it was a little better geometric match to what we had to get to, and also the large amount of metallic uranium provided a safety mechanism which is beyond our scope of our discussion today, but anyhow,
Jack,
was needed for safety.
How good of a simulation did you compare what a simulation section was doing compared to the actual fuel tubes? How good was the simulation?
Was quite good across the radius. Within a fuel element, it was not as good as we desired because our when we had 1 mil thick metal in there, and it was more of a point absorber rather than a spatial absorber. Mm-hmm. So we needed to have the other. So this is another representation of a similar core with the beryllium oxide core, the beryllium oxide reflector, and the places for the control rods to go basically near the reflector region.
And this type of thing was built up on the tables, right?
Yeah, we had those. We built 2 of the facilities similar to the one which we just looked at. One, the first one was a 6-foot square, and the other was an 8-foot square.
Yeah, this was a 6-foot square, I think.
Right. The first one was 6 feet, and then the one for the XMA mock-up itself had to be. We needed an 8-foot square. Actually, it was an 8-foot cube.
And an XMA reactor was a much more powerful reactor in tension. I know the heaters were around 20 megawatts. That was over 40, wasn't it?
I think it was over 100.
Over 100, that's right. Yeah. That's right. This was over 100.
Yeah, right. So now, during the latter part of the 50s and early 60s, the computational capability which we had available to us in terms of shield design, reactor design, thermodynamics, had just grown so remarkably that the critical experiments function was redirected to a large degree into some other areas. One of the areas was shield heating, which required a whole new kind of instrumentation, which we had to develop because we still had some problems in shield design, which required some experimental methods of measuring shield heating.
No, you don't need us.
No. So in summary, the critical experiments function these days, 1995, is very, very limited in as much of what you wish to need, that you used to need the critical experiment for, you can do with a very satisfactory amount of accuracy using calculational techniques. And there are very few reactor designs going on anyhow in the United States for any purpose whatsoever.
But you gotta admit that those were pioneering days.
Oh yeah.
Considering the fact that merely 5 or 6 years prior to that was the first critical experiment ever conducted. It's pretty interesting achievements that we accomplished.
Right. We had the first automated foil counting thing. We demonstrated in there where we could count the foils, the power of these catcher foils, which I alluded to earlier. Results were put out came out on a punch card machine, which we had in there in those days. This is the middle 50s. Punch cards were a big deal, big time. And take those punch cards down to a 650 computer and have the data reduced in a few minutes. Of course, it took you weeks to program the bloody computer. And then later on, we created a direct pipeline from our control rooms into the computer center. And when we came up, we did certain measurements, piped them directly into the computer, and this was in 1960.
Yep.
And we had an IBM 701, 704. And so that's basically the history of the critical experiments at A&P, where we went from very crude stuff, as you've seen, to hooking it up with the computer, which is the modern-day savior, I guess, to some folks.
And one other thing we might mention in closing, that these were real reactors. The fact that we only operated 1 to 10 watts doesn't mean they couldn't have been operated at 20 megawatts. Of course, they wouldn't have held together very long.
Oh, the very
the
large
capability was there.
Very large heat generation capability, very small heat dissipation capability, which means you get real hot.
Okay.
This is a model of the Convair NX-2 nuclear-powered aircraft. The NX-2 was never built. Its gross weight was about 500,000 pounds and was about B-52 in size. 3 XNJ-140 power plants were located inside the fuselage in a 3-abreast installation. Here the power plants were readily available for remote removal. Radiation shielding was used both around the reactors and around the crew compartment. Convair optimization studies were based on an acceptable crew dose of 0.02 rem per hour within the 5-man compartment. The crew compartment was located about 100 feet forward of the engines. A large part of the radiation striking the crew compartment is straight line coming from the reactor core. However, radiation scattering off the airframe and the air requires that shielding surrounds the crew compartment. The engine shield was designed to reduce radiation levels so that induced radioactivity of the aircraft parts did not hamper subsequent aircraft maintenance. Also, the radiation damage did not limit the engine-mounted parts. The XNJ-140, this is a model of it, was based on the direct air cycle, where compressor discharge air was heated in the reactor core in the uranium fueled area, and went out through the turbine and the nozzle. The OD of the side shield was about 9 feet. The power plant was 61,000 pounds, 2/3 of which was in the reactor shield area. The 183,000 pound weight for all 3 power plants was reasonable when one considers that the 747 might take off with 250 to 300,000 pounds of jet fuel. The 140 reactor power plant was a 4-bearing machine, the thrust bearing and number 2 bearing. The red indicates the annulus, which is the active core. The blue shows the front shield plug, the rear shield plug, and the side shield. The compressor discharge air flows outward, then down, and becomes a plenum ahead of the reactor. The mixed air temperature of about 1800 degrees coming out of the reactor and goes into a larger plenum and goes upward and into the combustor and the turbine. The duct configuration was similar to that of the Heater 3 reactor, which was tested in Idaho. The effect of the ducts on radiation leakage was not as severe as once expected. Neutrons are slowed down through a series of elastic or billiard ball collisions with atomic nuclei. The lighter the nuclei that the neutrons strike, the more energy they lose per collision. The slowing down or moderating process is vital to neutron shielding. This is because the materials for neutron absorption work best on thermal neutrons, for example, boron, cadmium, europium. The neutron shield materials in the XNJ-140 were borated beryllium with within the pressure vessel and lithium hydride in the outer shield, outside the vessel. These were chosen for thermal and mechanical requirements. Gamma rays lose their strength through collisions with heavy elements. This makes dense elements with high atomic numbers most attractive. Lead, iron, tungsten, tantalum are good. In the XNJ-140, borated 304 stainless steel in the front and rear shields absorbed gammas and suppressed the thermal flux. Cooling of the front and rear shields was by compressor discharge air. The compressor further reduced the straight line radiation to the crew compartment. This is a drawing of the front shield. The stainless discs are 304 stainless and 1 weight % natural boron are located close to the core, where they are termed shadow shielding. 550 pounds located there and a little parts up here. The beryllium of 1 weight % natural boron discs and sectors filled most of the plug and weighed 4,100 pounds. The Inconel X structure weighed about 1,000 pounds of the total 5,700 pound front shield. Secondary heating caused by gamma rays requires cooling of the shield. And the coolant bleed flow is from the duct here radially downward into a tunnel around the shaft going to the rear end to the rear plug. This is an isometric of the rear shield plug. The primary shielding material in the rear shield was beryllium plus 1 weight % natural boron. The shield structure was heat-treated Inconel X. A small amount of stainless steel with boron was used. The total weight was 4,400 pounds. The beryllium is again the larger volume. The beryllium inserts were placed inside the shaft at the aft end. They were aligned radially with the front and rear shield plugs, but not in the core region. There was 30 inches in the front and 43 inches in the rear inside the shaft. The inserts were positioned with torsional springs. This is the 140 radial or axial section of the core. The 2 bundle axial loads were contained on the forward end by 12 beryllium sectors, on the aft end by aft retainer. The latter consisted of 12 Inconel X twin tube sheet sectors. This aft retainer was internally cooled and externally insulated. It eliminated the need for tie rods going through the core to hold the aft retainers. The next chart is the 140 radial cross section. Red indicates the annular core and consists of the uranium-fueled beryllium oxide tubes. The side reflector is 8.5 inches thick and 90% solid with BEO hex bars. The beryllium oxide cooling tubes made up the other 10%. This reflector region also served as neutron shielding and somewhat as gamma shielding. Also, the outer reflector and the borated 304 pressure pads enclosing the tube bundle radially served as a thermal shield and limited energy deposition in the outer shield itself. Some neutrons were slowed down and were absorbed in the borated pads. This is an isometric of the side shield. It was outside of the pressure vessel and was cooled with ram air coming through here, going out there. It consisted of annular sectors of lithium hydride cast into 19.9DL stainless steel structural cans. Lithium hydride contained a good thermal neutron absorber, lithium-6. Like boron, it suppressed thermal neutron absorption in structural materials and minimized induced radioactivity in aircraft structures and engine components. The total weight of that side shield was 16,000 pounds. The thickness of this side shield through here, the thickness of that annulus, was about 17 inches. 1/3 of the weight was within structure, that 19.9DL material. The top forward sector is shown next. The ram air comes through the sector and exit out to another section. The next chart shows the internal cooling tubes that are placed inside this can before the lithium is cast into it. Shielding material was removed at the sides of the engines. This permitted an 83-inch centerline spacing among engines and shared shielding. At the left and right engines, shield cheeks were mounted to the airframe to minimize induced activity in the aircraft wings.
On the MTR, I worked mostly on the shield design, which was actually at the time one of the big uncertainties. The nuclear reactor design situation on physics was in pretty good shape. And where I worked there was right down there with Jimmy Lane, who was one of the big unsung heroes in the whole nuclear program. He was the guy that could calculate anything on the back of an envelope. And to get a quick, very close approximate answer to almost anything in nuclear or thermal or aero or electrical or anything. And he worked directly for Alvin Weinberg and then Eugene Wigner then. He's put in a few years down there, and that is when Wigner and Weinberg were putting together their work on the physics of nuclear reactors. Mm-hmm. Now, of course, people had to be designing nuclear reactors before that book came about. Yeah. There were reports that, for example, reports from the so-called Lexington project, which was an MIT AEC project, which we'll talk about later, where they'd had academics look at physics of shielding. And these were hopelessly complex discussions of the thing. But when I talked to Jim Lane about, how are we going to calculate the shielding, what comes out of the shields. When I got there, the shield configuration, external configuration, was already set. It was 7 feet thick of concrete, period. And we had to have air ducts go through that thing. So I asked Weinberg, where did that 7 feet come from? And there was no changing it at that stage of the game because they were already designing the foundations and one thing or another. He says, oh, well, Gene and I sat down one afternoon, we figured the shield should be 7 feet thick. So, you know, that's, yeah. So that's how it got to be 7 feet thick. Then we had to put in all kinds of penetrations, air ducts and control things and electrical conduit and et cetera, all within this thing. So I sat down with Jimmy Lane, and it turned out that, you know, on a quarter of a page he would do a calculation that I'd been looking at these academic reports and an inch thick, and you still couldn't figure out what in the world they were saying. He would just whip it off. And then I said, you know, where's all this stuff come from? And he says, oh, that comes from, mostly from a guy out at Hanford by the name of Wende, W-E-N-D-E. And he wrote a report out there on the shielding. And I said, oh, gosh, that's how they got shielding on the Hanford reports before they had all these academic studies. And he said, yeah, we had to have shields. Well, where did he get the stuff from? He says, well, you know, back in the 1920s in Helvetica Acta, there was a big issue devoted to the shielding of radioactive sources. And they took radioactive cylinders and cubes and one thing and another with different shield configurations around them and came up with all these very simple formulas, all starting with the inverse square law and with exponential random absorption. Beautifully simple. All that stuff really comes out of Helvetica Acta. You know, here's my copy of Helvetica Acta. And lo and behold, except for the problems of scattering around corners and in ducts, which they didn't get into very much, the basic shielding stuff was all done back in the 20s and very well written up, but completely lost track of by the academics who were trying to figure out the shielding later on. The mathematics they used for the simplest things, the academic stuff, was just, you just couldn't believe how they would mess things up. So in any event, I then went in to calculate the scattering through ducts and one thing or another, and we got a lot of experiments running down at Oak Ridge on the reactor, on the swimming pool reactor got built
the swimming pool reactor,
by that time. And so we ran the slab experiments of different kinds of shield slabs and combinations and of ducts and one thing or another. And so we got then the pretty well the shield design figured out. But in order to make the shield work, it turned out we had to put in big clumps of iron at one place or another and thicken up the shield here and there, and it ended up by being the most awful mess. And so we were bemoaning that fact. And then Ted Rockwell, who worked for Admiral Rickover, he was a very smart guy, just put out a book on the life of Rickover, a biography of Rickover, as a matter of fact. And I said, can't we just pour some high-density concrete in there and get rid of all of this patching that we've done? And he said, well, you could use barite. It has a density, ordinary concrete is about 2.4 or something like that, and barite has a density around 3.5. So we made believe we poured the whole shield full of barite, and we were able to eliminate all the patchwork and everything else, and it solved the problem, except for one thing. The contractor didn't count on having concrete that weighed 50% more than ordinary concrete, so he went broke on me.
Hi, I'm Mel Lapides. I was with the A&P project from 1952 to 1962. The Air Force actually set up 3 organizations for conduct of the shielding work on the A&P project. General Electric A&P, of course, was responsible for the overall design, development, and integration of the shield into aircraft. Oak Ridge was involved with both basic measurements at the lid tank facility and special measurements related, special facilities, I should say, related to the unique scattering problems of the aircraft reactor. Convair had similar facilities, but in contrast to a tower facility for scattering experiments, they actually flew a test reactor. One of the fundamental concepts of ANP shielding was that they really worked on two shields called a divided shield. You had the crew shield where the radiobiological effects of radiation on a multi-man crew were of major concern. Fortunately, perhaps, that crew shield was separated by as much as 100 feet from the reactor core source. The reactor, in turn, had front, rear, and side shields that were independently designed to different requirements. The overall concept of the divided shield was that this was a method of getting overall weight optimization. One of the distinguishing characteristics of the reactor shielding approach is suggested by a distributional plot of how the dose rate from either neutrons or gammas, not considering streaming immediately, varied with the azimuthal angle, where 0 would be horizontal to the core center line, would be the core center line. The dose builds up rather rapidly and then reaches a maximum at anywhere from 90 to 150 degrees. And what that meant was that the carrying shielding beyond this area was of perhaps limited value because it didn't contribute to scattering. I guess this must be scattered dose rate. Integrating the two previous slides gives you an idea of the philosophy of shielding. The crew shield, which would be over here, was the dominant parameter determining its shielding was separation distance. The front shield was what would be called a shadow shield to keep direct radiation from impinging on the crew shield. And that front shield was carried out only until the scattering, which was the other source of radiation to the crew, was no longer of benefit. You remember the line showing the azimuthal distribution. And so its weight optimization and benefit limit decided the size of the front shield. The rear and side shields were configured for provide radiation damage and activation limitations to facilitate maintenance. It isn't clear to me that the designs were highly validated, except at a very basics level. But it was of interest to note that they assumed very heavily that an awful lot of items in the aircraft would be replaced, and would be, even though that might not be normal practice in an aircraft at the time. I guess it's also worthwhile to remember that people were just starting into radiation hardening And certainly there were very few solid-state devices around at that time. I guess there are better radiation hardening systems, or systems that are more radiation resistant than semiconductors, but they certainly were not emphasized until much later in the 50s. So the trade-offs amongst all these parameters and defining the dose rate and the activation limitations for maintenance all contributed to the shield design, and that said the latter, other than radiobiological, dictated the side and rear shield design. I suspect that instrumentation somehow necessary for operation of the system may have been the most severe limit in the damage arena. We're going to shift now to some of the mostly pictures of facilities and equipment developed within the shielding program. The first and perhaps best known was the tower shielding facility built at Oak Ridge, and it was essentially a question of building a gantry tower or portable gantry tower so high and with such a minimal amount of solid structure so that you could loft a reactor and study its effect on a crew shield without being concerned about ground or air scattering, which turned out to be no mean trick, particularly since at the time people were not totally aware of neutron activation in air issue referred to as the nitrogen-16 issue. They also could test mock-ups of ANP shields. This is a schematic of the tower shielding facility to well vision. These, what I guess you call lacy girders, are of the order of 200 feet high. There's a swimming pool reactor down here, and this is a hoisting system for a reactor shield that is being tested. I believe that the reactor could also be lofted, as the case may be. These guy wires are what facilitated these very open, porous girders. Earlier, more conventional bridge work designs with a gantry crane up on top proved to give too much side shielding. And this is the hoist house, and the control room is over here. Here are two views of the tower shielding facility. This one shows the actual completed system, and I think right here is a mock-up shield being set up for test. This is the actual reactor system, which is a swimming pool reactor normally housed in this concrete swimming pool, and this is a self-contained reactor. The requirements on this system, of course, were that it be capable of lifting both the shield and the reactor system, so we're talking probably of the order of 10-ton capacity. The second special facility for the ANP program was the Conway Fort Worth Nuclear Aircraft Research Facility that became operational in '54 and ran through 1961. It was used for fuselage activation studies ground and flight validation of shields, and radiation damage studies. Shown here is the reactor and crew shield mock-up that were part of the NARF test program conducted by Convair. This was, I believe, used both on the ground and in the air. This picture shows a crew shield mock-up being loaded into a Convair military aircraft. The crew shield contained various detectors. And early in the program, the reactor was simulated by various gamma sources and I believe neutron sources, and then ultimately by the operating reactor shown previously. I believe it was in this series of testing that they truly discovered the magnitude of the scattering problem, including the nitrogen-16 issue. And of course, they were able to get information about activation and radiation damage by having sensors spread out throughout the plane. These schematics show the aircraft with the reactor and crew shield in place, and there's an instrument capsule between the two and additional instrument locations all along the capsule. That's a top view, and you can see a side view here. Somebody, not I, knows how they managed to protect the pilot during these flights. This shows the actual configuration of the crew shield where the operating pilot actually stood. He must have had great faith in shielding calculations, and or they ran the reactor up at power gradually.
My name is Art Ross. The facility that was done for using a chemical combustor to test the X-39 engine. In this there were large ducts connected with bellows, and here I'll just show you a quick picture which will be amplified later on for you. In that picture, there were two ducts that leave the X-39 engine and go to chemical combustors where they pick up the heat. These have expansion joints, which are large bellows, and you'll be able to see that better in the next picture. And every time the rods were tensioned, the big duct would cock out of line, and they kept retensioning and repositioning, and every time it cocked. And finally someone asked me to look into it. And it was a problem that I had come across in looking through theses I would use for my master's degree, I believe. And it was described by an aircraft company, Boeing, in Seattle. And they were suggesting it as a thesis problem. And what happens is it's a fluid column buckling in which columns supported by bellows or other expansion joints would buckle as if they were loaded axially, even though if the system is under internal pressure, even though there's no axial load in the system. A very unique and really hard to believe for most stress analysts problem. Well, we looked into this problem, and this turned out to be a case of fluid column buckling. And so we didn't have to reposition anything. We just put some chocks in that just held it, because there's really not much load to cock it. And that solved the problem for that. And as opposed to metallic components, ceramic components have no ductility, essentially have no ductility at room temperature, and therefore are very susceptible to thermal stress analysis. So when we started to design that element, thermal stresses became a very critical item in the design of the reactor, which was all ceramic. One problem, we had beryllium oxide, as I remember, I think of beryllium oxide reflector plates in the reactor. And we did experiments with these. They were non-nuclear experiments of the setup of the reactor. And when we opened it up, every beryllium oxide reflector plate had cracked. The normal two-dimensional analysis we had done for these would not have predicted cracking at all in the direction they were at. Wouldn't have predicted cracking, and certainly wouldn't have predicted cracking at the locations. And we looked at it as an end effect problem, and using some probably analysis that Gabe Horvey of General Electric Company in Schenectady, who I got to know very well later on, had worked on end effect problems, and I utilized an analog, mechanical analog to analyze it, and sure enough, a short rather than infinitely long reactor plate would have resulted in high stresses, higher than predicted by two-dimensional analysis, and in a direction different. And so that showed that the three-dimensional analysis would predict cracking. And also, luckily, it showed that all one had to do was use plates half as long, each plate half as long as the other, and the problem disappeared. So we did that, and it was needed no redesign because there were many plates stacked end to end, so we just had twice as many plates stacked end to end. Each plate in itself was cheaper, since the shorter plates were much cheaper to make than long plates. So we changed to short plates, and lo and behold, there was no problem. The last problem I'd like to describe is one that I don't think had been solved by the time I left, and this involved the ceramic fuel element cylinders themselves. Our present finite element analyses could have analyzed that in detail because they can solve nonlinear problems and three-dimensional problems. But at that time, Howard Eagle and I wrote an analysis of the stresses in the ceramic fuel elements using a finite element program, not a finite element program, a finite difference program, and as a matter of fact presented that at a GE Research Division symposium. During operation, I mentioned before, during operation, any solid piece of matter internally generating heat has to have stresses locked into it because the inner portions expand greater than the outer portions. It's like the core of a ball expanding against the outer surface of the ball. Nuclear energy is unique in that pattern that you cannot find a non-zero stress distribution. A non-zero stress temperature distribution. The problem that we had at the time I left was that the ceramic element could be brought up to power and run to power quite successfully. And if run for a long enough time, however, the stresses would relax, and at temperature there'd be no stress, which sounds great and is great. But the problem is that a reactor has to be shut down at some time. When the reactor shuts down and it comes back, tries to get back to its original shape, the zero stress condition gets stresses reappearing almost opposite in sign. So during operation, for instance, you would normally have compressive stresses near the center. When you cool it down, you get tensile stresses near the center. At operation, stresses are not important because they will yield and creep out and will not, the material is not brittle. But when it cools down, the stresses reappear, tensile stresses on the inside, and now they reappear on a cold and brittle ceramic tube.
One of the members of Art Ross's Applied Mechanics group is Howard Eagle, and we're pleased to have him with us today. And Howard, why don't you tell us a few things that you fellows were up to?
Okay, thank you, Otto. As Art Ross has mentioned, safety of the nuclear-powered engine was paramount, and if any failures were to occur, they should do so in a fail-safe mode. One question raised was, what would happen in the unlikely event of the airplane crashing into a granite mountain? We all know that airplanes don't crash, but what if? In such a crash, would there be time to sense the impact and scram the reactor? That is, could we activate and insert the control rods? Or would the reactor, as a critical mass, blow up the mountain and surrounding area? Since we were the resident dynamic experts, we were given the challenge. Working with Convair structural design and configuration data, we developed an analytical dynamic model of the aircraft and the nuclear power plant. Albeit it was a simplified model, as the computing capacity of that day was very limited. At the time, it served its purpose. We solved the initial velocity impact problem, which indicated the reactor control system would be able to sense a deceleration wave prior to the reactor itself crashing into the mountain. Sometime later, we constructed an even more simplified model using an equivalent thin-walled cylinder to represent the fuselage portion of the plane and a solid mass for the reactor component. We took the model to the D Street facility in Missile Space Division at that time in Philadelphia and used their shock tube to conduct a test. Tony Copa, at that time working in MSD, was working on dynamic buckling of shells and was happy to help us and perform the test. The test performed consisted of Tony firing a sabot from the shock tube into our freely suspended model. High-speed pictures were taken and accelerometer data recorded. This test agreed with an analysis we had made of the specimen and provided some credence to our airplane crash analysis. At the time the airplane crash analysis was carried out, there were, of course, skeptics that a crash could be sensed and a system activated, much less predicted through analysis. Let's fast forward the clock some 25 years and think of something common in our everyday life, something everyone comes in I don't think they come in contact with, but is aware of. That's the automobile inflatable airbag. Today, cars are analyzed using finite element dynamic models. Cars, complete with dummies, are crashed into abutments to demonstrate the safety of the airbag concept. And I'm sure we've all seen films of such tests demonstrating that impacts could be sensed and such control systems activated. I mentioned earlier that there was also widespread significance of our dynamic analysis methodology, and that occurred in the technology transfer of the programs that were developed in A&P. And I'm sure this happened not only in structural mechanics, but in other areas, thermodynamics, etc. After transferring to Philadelphia at program termination, Frank Krieger and I developed enhanced versions of the dynamic computer codes which we had developed and added new capability. Programs for stiffness generation, eigenvector, eigenvalue, or the modes and frequency computation, and response analysis to sinusoidal, random, and transient loadings became the cornerstone for dynamic analysis in both the reentry systems division and the space division well into the 1980s. The other divisions also in the company benefited from this work in dynamic analysis program development through the medium of the stress and vibration workshops, which were started in 1965 era when GE introduced the GE 635 computer that which later became the Honeywell 6000, and we shared between the different components of the company all the techniques that had been developed, and these were among them. The relatively brief history of the A&P program saw tremendous advances in the area of structural mechanics computations.